Good morning, everyone. Sorry for the small delay. For those of you who don't know me, my name is Marie Posma, and I'm the head of the Department of Cognitive Science and Artificial Intelligence here in Tilburg. And it's my honor to kick this event off. Welcome to the workshop of AI for robotics. And I would just like to thank the organizers of this event, particularly Giacomo and Murat, for bringing everyone here. It takes a lot of enthusiasm, I think, to get such distinguished audience to this very small city in the south of the Netherlands on such a rainy day. So thank you for making the trip here and enjoy the workshop.
So hi everybody, we are very happy to see so many of you here today. We organized this workshop, we started planning the workshop 1 year ago when we applied for funding from NWO, which is the Dutch national funding agency. They were kindly supported and sponsored the event together with Tilburg University. And the main objective of the workshop was to provide a venue for networking, in particular for networking between people working in artificial intelligence from a more computer science and the more robotics communities, which, however strong interaction they usually do, they're not as strong as they should really be. So with this event today, we want to put people together, introduce a fantastic lineup of speakers with fantastic talks ahead, and provide as many opportunities for networking, both during poster and coffee breaks and a lunch with some thematic stations. And we're also happy to invite you for drinks at the end of the workshop. We have a packed schedule ahead, so without further ado, I should rather introduce our first speaker, Francesco Nori. I am very happy to host him today. I have met Francesco Nori quite a long time ago, and I'm really happy that he could come today to visit us. Francesco Nori is a research director at Google DeepMind, and he manages a very large robotics lab there. And I really can't wait to see what he's going to tell us about the recent work at Google DeepMind. So without further ado, please welcome Francesco Nori.
Thanks, Giacomo. I have to say that I'm really excited to have this opportunity to share what we have been doing at Google DeepMind recently. Most of the things that I will present are published, so there are other things we're doing. We tend to publish everything we're doing, but of course we try to publish and present at public talks like this one, only the things that have been published already. But I have to say it's relatively updated, and I will hint on a few things. Clicker might not work. Let's see. Oh yeah, there it works. That's a little bit of the outline of the presentation, but let's go directly into the first part, which is just an introduction of my company. Well, Google DeepMind was founded in 2014, and actually joined Google in 2014, but in 2010 it was founded as a small spin-off of UCL. And then was joined with Google Brain, which is the AI division for Google, created in 2011, and then we joined forces in 2023. So it's a relatively recent merge that we actually went through. And I think that the scale at which we are operating now by joining robotics and AI in the context of machine learning has been quite major, and we are now a group of more or less 200 people working in robotics and AI. The idea of what we are trying to do is actually to solve artificial general intelligence. And I just wanted to bring up this slide because the generality is an important part of what I will present today. We know that for a certain number of tasks nowadays, we can automate through robotics the task itself. And this is very clear if you look at the cost of your iPhone, the cost of your car. And the reason why the cost is so low and it becomes consumer electronics, consumer hardware, is because we can automate the assembly process. But of course, it's not very flexible. Your iPhone is identical to the person you have on your right-hand side. And the cell phone, more or less, is the same. So it's very difficult to automate a general assembly if you want. That's why robotics in particular, and the things that we'll present today, it's all about generality and how can we make robots more general in the way we program them to do things for us. And that's important to keep in mind. That's another important slide that I always bring up. How do we make these tool that we're working with at Google DeepMind general enough to address the different things that we can do. That's an important part of what I need to present, so pay attention to this one at least. We try to abstract away from problems and from the specificity of problems by having a representation that can fit multiple problems. That's what it is. And the way we do this is by representing and using a representation that is very common in the machine learning community, and in particular in the reinforcement learning community, where you assume that you are developing what we call an agent. In control theory, I'm a control theorist by background, so in control theory will be a controller with state estimation and also the control part of the intelligent part. So it's the agent. The agent receives certain information from the environment and certain information that defines what task the controller has to do. And the agent can do actions in the environment. And as you can see from this slide, the environment can be whatever you think of. It could be a computer, for example, where you send clicks and you provide a few pointers position. And the actions, the observations that you get could be just a video that you're receiving. But if you are a robot, then it becomes more complicated. You have like a lot of possible actions. You can apply forces. You can apply movements, displacements. You get observations of different kind, like tactile sensing, cameras, and so on. And you can think of the problems you're working with every day, and you realize that this could be a good way to represent a sort of meta representation of what you are trying to do, especially if you are trying to develop a controller or an agent that works on a computer. So that works really well. A bit that is often underestimated in this picture is this, what I call task specification. How do I specify what I want this agent to do? Usually it's coded inside the agent, and we don't really put it there. It's not explicit. But in this slide, it has to be explicit. Because what we are trying to do at Google DeepMind is to be as general as possible in the way of describing what I want the robot to do for me, what I want the chatbot to do for me. And it has to be very natural. Initially, it was a reward signal that in control theory, optimal control theory is the cost function. But more in general now, we're looking at things, and I will present a few things initially, where it's all about text, images. And for robotics, of course, it's like the natural way we teach each other to do things, through language, through images, and maybe through kinesthetic teaching, by doing what I want you to do, right? So we are moving away from an engineer that codes a reward function or an optimal control function or decides what it has to do into the area where you want to just say the thing. You want to write it down. And it's a big change, and that's, again, connected with the generality. So let's keep that in mind. Big novelty, I don't think I need to describe this to you. Deep neural network are a way to describe these agents, and they're becoming extremely powerful in these days. I will say a few things about it. This is an old slide, so I don't think I need to go through it too much, but I want to stress on one bit. Language models are extremely very powerful in these days. You can play with them. You have Gemini, you have ChatGPT. Of course, I say Gemini because that's a Google one first. What I really care about in this slide is that somehow these language models understand the physics of the environment. That's an interesting one. Who have thought that this could be a possibility? Honestly, when I joined back when I met Giacomo, I was in the IIT, the Italian Institute of Technology, and language was all about, oh, there's no language without touching things, moving things, because language is grounded on our actions. Yeah, sure enough, but chatbots somehow can steal that knowledge from us by parroting what we're doing, generalizing over it, and they can make a sense of the physical environment and of the objects we are surrounded by. So that's kind of interesting. The bottom right box is the one that I'm basically hinting to. They know about affordances. They know what you can do with a potato, what you can do with a laptop, what you can do with a cookie, though. It's sort of already hinting on where I'm going, right? Language models can be used for robotics because they know about things. They know how to decompose actions into sub-steps, which is a purely robotics expertise, but was already coded in the language that these chatbots had the chance to see before being used. This is more to say that the tool is extremely powerful. Image generation, I know how many of you have seen or played with this kind of tools that are nowadays available online. So the one that Google released was blocked because it was unfair to sort of diversity in the communities. But there's plenty more running online. You can give it a try yourself. They might not be as accurate as this one because this is very, very pristine in the way of creating images. But what I'm trying to say with this slide is that there are image generation tools that are based on the ideas that I just described, that from the text at the bottom of this image, create the image on the top. And you see that the accuracy, but also the level of details and the level of modeling of the generative process without knowing anything about light, reflection, surfaces, and many other things that we thought were fundamental to understand how to generate images, can indeed generate all of these. Like top left is the one famous one because it's a transparent duck in front of a painting, and you see the reflections, you see the surface, you see many things that you can do with a rendering engine. But the fact that you can code everything without any law of physics from images, it's quite remarkable. This is the one that I added today, just because, again, I think it's an important one for robotics. This is Genie, is a relatively recent tool, this is a relatively recent neural network that we released. When we didn't release it, we published the paper. This is a neural network that can generate video games from images. So, of course, it has been trained on video games that look a lot like Super Mario, so no big deal. What is interesting, though, it's a relatively small-scale project. So imagine how to scale this up to a more complex environment. Small project in the sense of the amount of compute that was used to train this kind of neural network. But the video game on the bottom is actually a video game, as in order to get that video, you need to play with it. You need to have send actions, like in keyboard actions, to the video game. And it's created from the prompt, so from the images on top, which are synthetic images on the left, real images at the center, and sketches from kids on the right. From the image, you create a video game that you can play. What is relevant on this slide, and that's what I want to stress, is that you see the law of physics in there. You see that the character can, climb a ladder, can jump on a surface, and all of these make sense to us, clearly, but it's interesting to see that the deep neural network can also grasp the law of physics, the law of interactions, and can generate videos from actions, which again, for robotics, you can imagine is a big deal, because you can take one of these approaches and imagine, given the current view of the robot, you can imagine what could be the result of taking a particular action. What would be the reaction of me jumping off this stage, right? And it's giving us predictive capabilities that we know, for what we know about the human brain, are fundamental to act in the environment, the ability to predict what will happen, have a physics understanding of the environment. I'll be fast. I'll keep an eye on the time. So yeah, I'm running late on time, so I'll speed up. Why is this possible? Well, I have to say, I need to acknowledge a couple of things. One is our understanding of the human brain and how to bring this knowledge into the neural networks that we're using. Things like convolutional neural networks, which are inspired to the V1, visual cortex. Things like attention systems, coded in a very general way, in a very parametric way, is a fundamental ingredient to understand how information processing can be implemented into artificial representation of the neural network itself. The other big important component, I need to be fast on this one, is that the computing scale is really increasing in an unprecedented way. I need to make this example because I think it's very powerful. Any technology we live with today, if we think that in 2 years it will be 10 times better, we will be really surprised. Take a car, if I say in 10 years it will be 10 times more power efficient, then you'll be like, no way, it's impossible. 10 times is already kind of a big deal for any technology we're surrounded by. Well, in this slide you see that a compute in the last 30 years, well, this is just in the last 5 years as a matter of fact, but increased by 10 to the power of 15. So it's a blowing number that I can't even myself make sense of. But computing is becoming a very cheap technology, but also getting close in terms of the size of the memory and the representation that we have. And it's at the bottom of this slide. It's very close to the human brain. Let's face it, like it's really the case. The number of connections we can realize nowadays on a relatively small NVIDIA GPU, it's comparable to the one of the human brain. So let's face that technology is getting really close, and it will be possibly better in the future. So that's always to keep in mind. Oop. Let's dive into robotics. How am I doing with time? Okay. Well, I present today GDM Robotics today, so Google DeepMind Robotics. We have a bunch of investments, mostly in dexterity and agility. We work with models and algorithms, the one I just described, so representation of the neural network. We work with simulations. We have a tool that you can use. It's called Mujoko, is a tool for robotics, is open sourced, so you can really be part of the open source community, but the core of the developers of this tool is at Google DeepMind. They're good friends of mine. If you have any trouble with bugs, something that doesn't work, reach out to me. As Giacomo was mentioning before, since he visited my lab recently, we do have a quite scalable, that's the term we use, but it's quite massive lab full of robot arms, doing many things, but mostly collecting data. As you can imagine, that's an easy one. These approaches are very data hungry, but also evaluating continuously what we are trying to do. So it's not just data generation per se, but it's also a big component of, if I have this neural network, is it really doing what I'm supposed to do? Yes, we use a lot of simulation, we use a lot of other things, but the proof that what the robot has learned is the right one requires evaluations and tests. So it's basically a bunch of robots, robot arms, industrial arms, playing with toys in front of them to check whether or not they learned the task they were supposed to learn. A few things that we have worked on recently. I just skimmed through a few papers. As I said, simulation is an important part of what we're doing. Data is difficult to get from real robots, so an easy way to do and to go about it is to learn from simulation and transferring on the real world. And I think, I don't want to enter too much in the details because actually the next video is a bit more interesting. But we can solve tasks as complex as the one you see here. The humanoid that you see in this picture, the black small humanoid, is tasked with a couple of things. On the left needs to navigate in the environment, avoid the obstacles, and go to different locations in the area. And on the task on the right, the humanoid has to push the basketball ball into the green box. What is interesting about this paper is that the agent just sees images and from the camera, from the first-person camera, and just controls the joints of the robot, the movement of the joints, and produces everything else it will see. So in order to do this, the robot is estimating its position in the environment, the presence or non-presence of obstacles, and then it needs to plan for footsteps in order to avoid the obstacles and get to the target. Or in the right-hand side, even estimate the position of a moving object in the environment, in this case, the ball. I don't know if you have a video. Hopefully I do. Oh, there you go. You see a few things. Top right, that's the first-person view of what the robot sees. And then you have an overall view of what the robot is eventually doing. So as I said, in these videos, you have a lot of estimation, understanding, planning, and many other things that typically you need to have in order to solve this kind of task. This is the bull pushing task. Again, you see very low resolution, but enough for the robot to see the ball, locate the ball, go around the ball, and then push it in the right direction. We took this to another level by playing soccer, and we do the same, and that's very mesmerizing, so I'll just dive in directly into the videos because this is pretty good. Again, I'm not entering into the details, but it's first simulated, so that's the simulated environment, and then transferred into the real robot. There are a bunch of techniques nowadays to do that. They go under the name of sim-to-real transfer. Final result is pretty astonishing, so I want to show it to you. Again, same idea. Trained in simulation with very simple reward for just winning the game. That's the reward we give. We actually have a bunch of intermediate skills, we call them, like dribbling, kicking, and many other things. But this is real time. You don't get to see many real-time videos nowadays in robotics. Not specifically at Google DeepMind, we don't have many real-time videos, I have to say. I think Giacomo saw the video live, and you can trust, if you don't trust me, trust him, that it really works this way, and it's fun to watch. You can watch them endlessly and have continuous fun of saying, oh, look at that, look at this other thing. It's extremely entertaining. This video is on YouTube, and you can definitely have a look at it. Let me just stress on one thing at the beginning. There's an interesting strategy, which is just after this video here, this clip here, kicking the ball on the corner in order to avoid the opponent. So kick the ball in the corner, get it back, and then kick on the goal. I think that's kind of interesting. Remember what I said at the beginning? There's an important component about generalizing with language, and that's what we're doing now. The soccer task is interesting because it's very dynamic, but there's nothing about what I told you before. So we want to instruct the robot in a more natural way. The way to do it is through using large language models in conjunction with actions, and that's what I will just go through briefly. In particular, one approach that we did is called RT2. It's a little bit of a busy slide, but what you can get from this slide is on the left-hand side. We basically took one of these language models you play with, ChatGPT, and we added a few tasks. So you see a few tasks on the top left are the natural one, question and answering, like what is happening in this image, and then a great donkey walks down the street. Then there's French, there's a bunch of language tasks themselves. And then what we did is adding a bunch of similar data, but in this case, the data contain movements of what the robot is supposed to do. So in a sense, you couple language knowledge together with grounding into what it means to do certain actions. And you see it on the bottom left. What should the robot do to, and then it's parametric on the kind of task, to fetch the crisps from the drawer. And then you have the answer is actually an action that you feed to the robot. And then you basically do this approach and see if there is any transfer from the language capabilities to the motor capabilities. And that's what we observed. I will just go briefly through these numbers. But what you see in particular on the right-hand side of this slide is that we can perform unseen tasks and generalize actions that have been seen in a particular context into new contexts. And then I will conclude with one paper that we published before actually merging with Google DeepMind. It's similar in essence to what we have seen and presented just before. It's extremely focused on robotics and has particular type of assumptions. One important bit is that, again, we need to provide demonstrations of the task we want to solve. In this case, there are a bunch of assembly tasks. You see the gear assemblies. They are collected by asking people to solve the task through teleoperation. What we do is, represented in this slide, is we keep iterating this process. So we start with collecting some data. We try to solve a certain number of tasks, possibly new tasks. We collect new data by letting the agent try to solve new tasks. We filter them, seeing which one of these processes is successful, and then we spin the wheel, as we say. So we keep feeding the data created by the robot to fine-tune and improve the performances in new tasks that were not initially demonstrated by the teleoperators. And we did this at scale. So you see there's a variety of tasks happening here in a relatively simple environment where you have a parallel gripper, so it's a claw gripper with 2 fingers grasping an object in a small contained basket. But you see a bunch of objects that can be used, from simple blocks like the one kids play with, to gear assembly, as we call them. This is inspired by a benchmark proposed by the National Institute of Tunnel Technologies, and even to simple grasp actions on natural-looking objects like vegetables. And we also do this with different type of arms. That's, again, we bring in the generality. So we're not just focusing on one robot only, but we try to do many different, what we call embodiments. And that's another task. It's what we call shape matching, anyway, no big deal. So what we did was to massively collect a bunch of examples of tasks and demonstrations with these arms that were in the previous slide. So the one on the bottom here, simulated and non-simulated. It's a relatively massive data collection. And then we attempted to solve new tasks. Not only new tasks like the one on the left, where you are, for example, putting vegetables into a cup, or you're trying to match shapes into a game, a kid game. But also we try to use very different embodiments. The one on the right-hand side is a new hand, multi-finger hand with a lot of dexterity, similar to the human hand. Completely new. It was not in the data we used for training the first agent, so it's what we call a held-out embodiment. And we asked to solve the similar tasks, and long story short, we got a good success in that sense. I think it's in the right-hand side, so probably, yeah, there you go. With just 1,000 demonstrations of the new task, we could fine-tune and specialize this, what we call generalists, so a network that can do many things, to the new task. And I think, yeah, I have a small video that we'll skip because it's online, and I think I can go to the conclusions. Yeah. Well, I think that I was trying to sort of describe how I think that deep neural networks can represent complex control actions, that these controllers can be learned on real systems. Learning of this system requires additional information. We either use accurate simulations or first-person demonstrations of the task, or multi-agent learning, as we've seen in soccer. And I think there's a hope that large neural networks can really represent a large amount of behaviors, not just language, but also including actions. Yeah, and that concludes my talk.
We now have some room for questions.
I have one over there. Yeah, you have the microphone on the side.
Me? Lucky me. Right. Looking at the football playing robots, there is some understanding of physics in those systems, in those huge parameter space. There is some understanding of gravity, and there is also some task-specific insight into how to solve the 1v1 football task efficiently. Now, I see a lot of opportunity here in this type of systems to inform our own insight about the physical world. So, except for what we know about the 1v1 soccer match, gravity, and different football tactics, maybe the robots can inform us back about, let's say, the structure of the universe, or the structure of the task. for us humans to get new insights about how this whole thing works. So my question is, what can you tell us about the opportunities of deep learning and reinforcement learning in robotics for automated scientific discovery? And what's Google DeepMind's interest in this type of problem?
Yeah, thanks. Yeah, it's a very good question, actually. Well, my CEO, so the person that initiated all of these pivoted the company exactly in this direction because he thinks that that's a good way to go ahead with using these tools for advancing science. I think in general, what I can say is that Demis, my CEO, is extremely, extremely fascinated by science fiction. And that goes exactly in the science fiction direction. How can machine learning or this AI help us in doing things? So I think that in terms of what we started from, soccer, yes, I think you're right. There is an understanding of physics, but the point is that the understanding of physics is very limited to the task. So it understands the physics of the ball, it understands the physics of balancing, but it doesn't understand the physics of, something else touching another object. Like, it's very limited to that narrow domain. While our understanding of physics and the modeling, even Newton, what he was trying to do is to find one model that fits multiple things. And this is missing. That's clearly missing in that video. That's why we want to look into generalization. We want to feed more examples of the physics we know about to have hopes that at a certain point this will generalize. And I think that possibly the first thing that we will see is that we humans have a very stereotypical way of doing things. And it's mostly related to our way of exploring the world of physics. The good example is like a high jump, right? So, for a long time, high jump was done with a different technique. All of a sudden, it was discovered there was another way to do it, which was more suitable for the physics of the human body. I think there's way more than that. There is like a lot to be discovered, how to use physics at our advantage that we could really learn from embodied agents acting in the environment. Examples of this, and then I need to sort of shorten the answer. Chess, you probably know, AlphaGo is a famous chess player, of course, synthetic chess player. Nowadays, people study AlphaGo before going and playing chess because it's useful. It really discovered new openings, it discovered new strategies. People are using these strategies. It's a very simple, narrow domain, but still it's happening. Similarly, protein folding is something that we've been doing a lot. This is a tool now available to everyone. Just long story short, if you don't know what this is, it's called AlphaFold. It's an AI that can take a sequence of amino acids and produce the 3D structure of the protein that results from that sequence of amino acids. It's used to do drug discovery and understand how proteins interact in our body. The point is that doing this prediction of the 3D shape is a very complicated task and usually takes up to 4 years, while now we reduce this down to a day. In a day, you can know what is the shape of a protein, and you can do synthetic drug discovery. This is already started a couple of years ago, and now many startups are doing it. I think I need to cut this answer.
One more question?
Possibly another question back there.
Well, you made a very compelling case for deep neural networks. I wonder whether you think that there's still room for traditional control engineering methods in the future, like, for example, to provide safety constraints or in lower layers of cascaded control schemes like velocity control, force control, current control, or do you think that all of this should eventually just replaced by just more networks?
I mean, it's a tricky question. Thanks, Heike, by the way. I didn't notice you. I noticed during the talk you were in the audience. I mean, the solution will be in the middle, for sure. But what I'm fascinated as a scientist now is to explore this uncharted territory with a lot of new things that looks very different from what I'm used to. I come from this approach to robotics, which is extremely model-based, extremely structured, and I think there is a lot of value still. Even daily at Google DeepMind, I need to use my knowledge about model-based robotics to remind the importance of tactile, of physics, of understanding the basic principles of physical interaction. But I see that there is a lot of fascination to discover this uncharted territory, which is nothing to do with physics, nothing to do, it's just data intense. The solution eventually will be in the middle, but as a research scientist, I think it's just important to explore this amazing area of science that is so new at the moment. If there is time, I don't think there might, yeah, there's no time for, I'm happy, I'll stick around for the whole day, and also we're going out with Giacomo for dinner, so I'll be happy to answer for other questions live.
We're also going to have time to ask questions during the coffee breaks and during the panel discussion at the end of the day. So there will be plenty of opportunities.
So welcome everyone again. And now we are moving to our second speaker, Jens Kober. And I can give a brief introduction to him, but if I am missing anything, please correct me, Jens, during your talk. He is currently an associate professor at TU Delft, at the Cognitive Robotics department, which inspires us a lot. Okay, and our department head is also here, and now I am declaring that we are also moving in that direction. And Jan's background is robotics, and he's working on sensory motor learning, reinforcement learning, and he's owner of a lot of awards, and many of them are inspiring. For instance, he got Early Career Researcher Award from RSS, Robotics Science and Systems. He's also owner of the Early Career Researcher at IEEE. And I can give a few hints about him for the PhD students. He's also owner of the Best PhD Thesis Award in Europe. And I have a bit interesting connection with him. In 2011, he published one paper which inspired me to actually work in the robotics. The paper title, Reinforcement Learning, title is Reinforcement Learning for Adjusting Robots' Movement for New Situation, with Jan Peters and Erhan Öztop. So I'm sure he will do a lot of interesting, introduce a lot of interesting stuffs. So without going too much detail, Jens, please. You can do it.
Thanks a lot for the invitation and the very kind introduction. And it gets even worse in terms of connections. We also used to have an Air Lab in Delft, which stands for AI in Retail. I'm going to show one video later today. But now we're done with that project, so you're free to have that name. Oops. It's actually going to connect very nicely with what Francesco was talking about. I'm going to take a slightly different stab at robotics and learning. What I'm going to talk about today are really specialists, but with the idea of being able to learn so quickly and directly on the real robot that you don't need to go through the effort of collecting massive amounts of data, doing lots of learning in simulation, and having very big networks. But I think there's lots of also interesting ways on how you can connect them. Okay, so just a little fun illustration of what I'm interested in. It's also motor skills. Francesco had that on one of his slides. So that's movements on the order of a couple of seconds to maybe a minute. So something like flipping a pancake or a kick in robot soccer, that would be one motor skill. And then you would chain those to achieve more complex tasks. That's not my laptop, so it's not my fault. Maybe you need to plug in the power. Okay, let's see. Yes, no, maybe, good. Francesca already mentioned collecting demonstrations and then having the robot imitate that, so it'd be imitation learning, or robots having their own definition of success and then practicing on their own, which is reinforcement learning. And that's also very much connected to how humans learn. What I'm going to talk about today is also inspired by how humans teach and learn. That's interactions with teachers. So if you think about a little child, he or she is going to interact constantly with its caregivers, who are going to provide encouragement and feedback and instructions. And the same if you're learning a new sport or learning to play a musical instrument. So that's teaching through interactions, where the idea is that you are going to have some form of intermittent interactions with a teacher or a coach. For instance, additional demonstrations or providing some kind of feedback while you're actually still learning. And that's something you see more and more in robot learning. I believe there are big benefits to approaching robot learning in this way. It's drastically speeds up the robot learning, which enables the robot to learn more complex tasks. And hopefully that's also a somewhat intuitive way for humans to interact with robots. And we're actually quite good at that. And it's not only other humans, but also other agents where we apply these kind of strategies. I'm going to first talk about applying this idea in the setting of reinforcement learning, so learning by trial and error. And then the second half of the talk is going to be about applying that in imitation learning. Before we do that, I'm going to show you a very old example on reinforcement learning, learning to play ball in a cup, so to catch the ball in the cup. My cousin's daughter was around 10 back then. Took her 35 times to achieve the task. For an average adult, that's maybe around 20 or so. Also here we started with providing an initial demonstration. If you just mimic that and play it back, it kind of works, but it still misses by a few centimeters, and then it starts trying out different strategies. It gets closer after some 40, 50 trials or so. It usually bounces off the rim, but sometimes goes in, and after 100 trials or so, it has converged. So roughly same order of magnitude as human learning, and we were quite proud of that back then. And in a few minutes, I'm going to show you how you can do even better if you include a human teacher in the learning loop. Okay, so how would that look like? I can go very quickly over that because it's exactly the same thing rotated 90 degrees that we saw a couple of minutes ago. So we have the environment, states, actions, and the robot has a policy that decides on which action to take in every state. You could have a reward or cost or goal definition there additionally, but what I'm going to focus on is having a teacher there additionally. He or she is going to be able to observe both the states that the robot and environment are in and the actions the robot takes. And now what the teacher is supposed to do is provide some kind of feedback to the agent. You could go to two different extremes there. You could say, let's just have the human teacher provide an evaluation. In the simplest case, that's just binary. Success, 1, failure, 0. It's probably very easy to do for a human teacher, but then you get the typical problem of having very sparse rewards in reinforcement learning, so it's very tricky for the robot to get meaningful information out of that and explore on its own to get the one success. On the other end of the extreme, you would say, let's just have the human teacher provide the perfect action the robot was supposed to take in a certain state, which can also be very demanding for a human teacher. So the examples I'm going to show you in the following are somewhere in the middle, and what I also have here on the slide, we're going to have corrections. It's a correction on the action, so it's saying you should move more to the left, more to the right, move faster, move slower. So it's more like a gradient and also not telling the robot the absolute offset, but just a direction in which it's supposed to change. Many of the things are based on an idea from an algorithm that one of my postdocs developed. It's called COACH, Corrective Advice Communicated by Humans. In this very simple illustration, the idea is the robot drives down from the top to the bottom on the right side of the road. It has some initial policy, it's not great, but then you have the teacher who is jumping in once in a while, providing corrections, literally move to the left, move to the right in this case. It's going to integrate that into its current policy, and hopefully the next iteration is already going to do a lot better, and the human needs to jump in less frequently. And then in the end, hopefully the robot or little car in this case can do the task on its own. So coming back to the ball in a cup example, we could say, okay, let's replace the initial demonstration, for which Katharina, my colleague, actually also had to practice quite a bit to get it right, by using this kind of interactive approach of correcting the robot's actions and coaching it to do that successfully. And then let's fine tune it with reinforcement learning again. But we can actually do better and do all in one combined approach. For reinforcement learning, one of the important components is exploration, so the robot trying out new strategies to see what works and what doesn't. Very classically, that would be some random exploration using a normal distribution or some Ornstein-Uhlenbeck or whatever. So now what we did here in this paper is we also modeled the interactions with the teacher as a form of exploration, and that allows us to very naturally integrate that into a fairly classical policy search approach. Policy search, so that's effectively actor-only reinforcement learning, where you're directly trying to optimize the policy in an episodic setting. Looks something like this. I don't think the laser pointer is visible, so I'm just going to very quickly talk you through it. So you do multiple iterations, you try the same task multiple times, you do some exploration, so you modify it a little bit, and then in the evaluation step, the robot figures out if the thing it tried worked better or worse, and based on that you update the policy parameters. So that's how a typical policy search approach would look like. And now what changes if we do that interactively is that we have the option for the human teacher to jump in and to provide corrections. We have a hard switch there. If the human jumps in, then we're going to switch off the autonomous exploration, because it tends to get very confusing for a human teacher if the robot is trying random stuff while you're still trying to correct it. And what's also very important, what we figured out, is that as a human teacher, you can directly see the effects of your correction. So if you press a button to tell it to move more to the right, it should directly start moving more to the right. That really helps to figure out if your correction was successful, and to get the policy to improve. So it looks something like this. Now we can actually start from scratch. So initialize it hanging down without any initial demonstrations. What you can see is Carlos sitting in front of the robot using a keyboard, providing these corrections on moving in which direction a bit more, and the velocity. And then after some 20 trials, it can actually catch the ball in the cup. And here's a little slow-mo. So if you look then at some plots, we have on the x-axis the number of rollouts, so the number of times it tried to do the task. And on the other axis, that's the cost, so lower is better. In red, you see what happens if you try reinforcement learning from scratch, just using more or less the distance between the ball and the cup as a cost function. It takes some 200 trials or so. It was a lot faster if you kind of initialize it with a good initial policy, and it just needs to fine-tune. In green, you see what happens if you use only the interactive imitation learning. So it's just a human teacher providing corrections, but the robot not trying to optimize it on its own. And in blue, that's the combined approach I was talking about. So you can see that for both interactive approaches, it learns very quickly in the beginning, so some 20 trials or so. But then for the green one, if you look at the end, at some points, it just flattens out because the human teacher reaches his or her capacity of how fine-grained you can do the corrections. And if you combine that with the robot doing reinforcement learning on its own, you can see that we get a better final performance. Initially, it takes a tiny little bit longer, but it's actually compensated by having a better performance in the end. So that really plays to the strength of both the robot and the human teacher. You mentioned high jump. Kind of a human teacher would be very good at figuring out the Fosbury flops or the new strategy. And then the robot is very good at doing that very reproducibly and actually fine-tuning the movement. And then what you also very nicely mentioned, one of the big kind of assumptions we make here is that the objectives of the robot and the human are aligned. If the human teacher is trying to provide corrections that go against the optimization criterion of the robot, then yeah, you're going to be in trouble, and it's probably just going to slow it down quite a bit, and you won't profit from the inputs of the human teacher. So that much on using reinforcement learning with a teacher in the learning loop. And now I'm going to switch to imitation learning. So there the setting is that whatever the human teacher demonstrates, that's by definition the correct thing the robot should do. It does not have any own objectives. It's trying to optimize in parallel, maybe except for some lower level safety layer stuff. So also here we try to learn directly from images using a comparatively very simple neural network structure with a few convolutional layers going to a compact latent representation. That's the part in purplish there. And then we have image reconstruction, so kind of an encoder-decoder structure as one of the auxiliary criteria, and the main objective is to learn, again, the policy, so which actions to take. You could go the way of saying, okay, let's pre-train the kind of the perception to get a good latent representation, which would mean you need some data related to the task beforehand to train that, and then once that's kind of converged, you start training the policy. Turns out it's almost as efficient to do it directly in this combined way, and the final performance is actually better. So why is that? The thing is, initially the robot doesn't know anything. It doesn't know how to do the correct behavior. So effectively, in the beginning, the human teacher is going to remote control the robot anyhow. And by the time it has learned how to mimic the actions of the human teacher sufficiently well, also the perception part has converged sufficiently, so that very nicely plays together. So how does that look like? Here's a little example in Duckytown, one of my PhD students using a keyboard, which you can see once in a while to provide the corrections. On the top you can see the very bad camera image, on the bottom you can see the even worse reconstruction thereof. In this case, we really did not care about the quality of the reconstruction. It just needs to be good enough to be able to do the control. So you can see whatever the lane markings and boundaries, and everything else is very blurry. And then what you can do is actually some kind of instantaneous validation. Take your hand off the keyboard. You see how well the robot behaves. If you're happy, great, you're done. If not, you just continue providing a few more corrections. So within really a couple of minutes, you can teach a robot to drive there. That was without any real interactions with the environment, but things become more interesting if you actually are touching things or you have high-speed movements. In the next approach I'm going to show you, we actually wanted to not only learn the trajectory and actions of the robot, but also the stiffness parameters so it can exert forces on the environment. There we started with a kinesthetic demonstration, taking the robot by the hand and moving it around. Because we didn't have a force torque sensor, they are kind of recording the precise forces and interactions wasn't possible, and that also doesn't work for correcting it that well. So once we have this initial demonstrations, we actually switch to a different interface. In this case, it's going to be a space mouse. And what the robot is learning is at the same time a trajectory. So that's the part in blue. So it's an attractor field using a Gaussian process in this case, and a stiffness profile. So that allows us actually to have a stabilizing field that pulls the robot back to the nominal trajectory. And I'm going to show that in a second. So here's a video of a very classical whiteboard wiping task. Anna is providing 2 demonstrations in this case. If you play it back, you can indeed tell that it didn't figure out that it needs to apply a force or have the attractor of the controller below the surface. Now she is going to push down on the space mouse to indicate it needs to move more lower, and at the same time what you saw on top here is it's adapting the stiffness parameters of the robot. So that was just 1 iteration of corrections, and then you can try that out, and it already works. Then that's the Air Lab example. You can see it there. It's about restocking in a supermarket setting. And there it's really all about speed. So we wanted to get it down to below 5 seconds. Now it's still sped up. You can see yet another interface we use for the corrections. So it's a kind of game controller. And what we're doing here is we are correcting both the trajectory and the velocity separately. One other interesting tidbit is that the timing of the robot gripper is very inaccurate. It's plus minus half a second for us. So also there, the teacher needed to come up with a strategy that is robust to the exact timing of when it closes the gripper. Okay, and now here in real time, putting the milk carton in the shelf. There we also did a few experiments and user studies in a slightly simplified setting. If you have some kind of perception there, it can also adapt to the movement of the objects. And because the behavior is based on uncertainty, if you move away too far from the data it has seen, it becomes so uncertain that it just stops until you bring the object back and it knows again what to do. So those so far were tasks a bit in isolation. We also participated in a competition last year and the year before, which is about solving these kind of task boxes. This one is vaguely inspired by disassembling and recycling electronic products, which has many, many different steps in there. So here, one of the steps was unplugging and plugging it in somewhere else. What you're going to see here now is it's also doing some kind of a recovery behavior, spiraling. Many of the tasks are very precise, so actually there really visual feedback is needed as well. And again, start with an initial demonstration, and then we use a couple of rounds of corrections to get it there. And then we combine it with these additional modules and some higher level sequencing of the tasks. Here is a video of the complete run. I probably won't be able to show all of it, so that's now in real time actually. So one of the cool ideas our human teacher came up with is not having a specific gripper, but actually use the cable in this case to open the lid. Now it's going to do the plugging in. Okay. What else is there to say about it? So in a moment it's going to take out the probe there. Taking it out is obviously fairly easy. Getting it back in was surprisingly challenging. You can't really see it. It's like a hole in the middle and another circle around it. So if you get the tip in the circle, then it gets stuck. And they need to be a bit more smart about detecting when it goes wrong, or learning to detect when it goes wrong, and then fixing it. And the final part, which we actually thought would be very hard, but turned out to be very easy, is wrapping the cable around these 2 hooks you see a bit on the left. Okay, in the sake of time, I'm going to wrap up the talk. That video is also online, so if you're interested, you can see that on YouTube. So, to sum up, I was talking about teaching through interactions, and I hope I could convince you that this is a very promising approach for speeding up robot learning, especially if you're focusing on experts and narrow tasks. it really plays to the complementary strengths and weaknesses of human teachers and robots, but I also believe that can be very nicely combined with many other ideas you have in robot learning, using a large language model to come up with the correct sequence of doing things, pre-training stuff in simulation, using these kind of methods to collect better and more data for training generalist models that Francesco was talking about, and many, many other ideas. We wrote a massive survey paper on interactive imitation learning a year ago, roughly. So if you're interested in this topic, feel free to check it out. And one big open question is still really, how do humans like to teach a robot? We've done quite a few user studies, but that was really more about figuring out if our approaches work. But there we really saw a big difference is in how human teachers approach it. People that play video games tend to be very good at teaching robots in that way, but also in terms of preferences on how much information you give, how many options you give them, how many different ways of controlling and interacting with the robot. That differs very much and is a very interesting challenge. With that, thanks a lot for listening. You can see my team and other people that contributed to work I got to present today on the left, and on the right you have a few logos of the sponsors. Thanks a lot.
Let's see if this is on. Yeah. Thank you for the talk. It's really impressive to see how fast you can teach these different robot manipulations by just doing imitation learning. But I have a question. So we saw in the previous talk by Nori that we are able to use large language models combined with some sort of perceptive system like a visual transformer to then output what actions the robot needs to take to complete the task. So are you exploring any kind of ways in using the large language model to tell the robot how to improve?
Yes and no. So we're definitely exploring large language models. Who isn't? At least the things I've seen and experienced is if you have this kind of a generalist model, it works fairly well to get it roughly right. But as soon as you get into the really nitty-gritty, highly dexterous tasks, what you get as an output is very good as a kind of a starting point, and then you can use these kind of approaches to fine-tune it. So that's really more on the lower level, on the level of a single skill. Where I think they really excel is in figuring out kind of the longer horizon strategies on which individual steps you need to take, and yeah, we've been working on that definitely.
For the tasks that you showed, humans could also execute those tasks, either with a remote control or by guiding the device kinesthetically. What you do for tasks where probably the person has a generic idea what to do but can't really execute it? Would you just scale it in space or time, or do you think that there's a better way of translating?
Very interesting question. So I didn't show that example. Actually, you can to some extent teach tasks in this way that you can teleoperate. One very simple example we did was on a pendulum swing up and balancing task. The one we had is really so quick that you can teleoperate it, but by having the robot in parallel kind of do whatever its rough policy it already has, and you can really focus on the corrections, you can teach that. Obviously, that has limits, and indeed, there could be ideas like doing it in simulation first and slowing it down, or trying to figure out different interfaces where you don't have to focus that much on the really low-level real-time control, but providing more higher-level general strategy. That would be very interesting indeed.
Yes, thank you for the talk. I had a question because we can see that if the teacher knows how the action will look like and how the action should be done, then the robot won't actually search for the space for another path that's different from the one that the teacher says and kind of guess a more optimal way around it, right? So how can it compensate for that if it does?
Yeah, okay. So it's a form of a trade-off. So the second half of the talk where I was talking about imitation learning, there the robot doesn't have a notion on its own or no ability to judge how well it does or not. What you see is that people will start trying out a certain strategy, and then maybe you figure out, okay, it doesn't work for the robot because of, I don't know, some limitations on the speed or the joint space, or I don't know what. And then people are usually very good at just pivoting and trying out something else until you find something kind of in interaction with the robot that works. If you're really talking about the reinforcement learning part, where the robot also tries on its own to optimize for something, then you have to trade off between how autonomous the robot is, kind of fine-tuning a movement that's typically very efficient and fast. But that then also obviously means that you're stuck in the kind of the local optimum that the human teacher has pushed the robot into. Yeah.
Okay, thank you.
Any one last question?
Great, thanks for the talk. So you show that you integrate the demonstration into the interactive reinforcement learning method. Yeah, so I was wondering, like, do you think in the long run, if we have enough demonstration, for example, like internet level, internet scale, robotics demonstration, then we will only need like imitation learning or learning from demonstration? Do you think that that's possible, or we still need like interactive teaching or with a
jury is still out on that. I mean, there's lots of efforts nowadays on collecting indeed internet scale kind of equivalent amounts of data for robots. I mean, the big disadvantage is that you don't have any information on actions on YouTube or I don't know where else. So that really needs to be collected by robot labs. And then the RTX initiative by Google DeepMind and others is going that direction. So far, at least, what you can get out is, like I was saying before, a kind of a good initial rough movement, and then you probably still need some fine-tuning in some form or other. The other thing to consider is, especially if you're thinking about a more industrial setting where a company might not want to share all their data for these kind of tasks, it probably won't work as well anyhow. I think it was the last question, or one more, I know.
Are you also able to give the robots more abstract feedback, like this is better than the last one, or?
Yes, yeah, we have tried quite a few things, so you can get the kind of really binary feedback, success, failure. You can do kind of a comparison between different runs and say this one was better, this one was worse. And then what gets really interesting is actually thinking about combining kind of these corrections and these more high-level general kinds of feedback. We've done some work on that. In the theory, works out nicely, and if you do it in simulation with a simulated teacher, that also works out nicely. Where it gets a bit more hairy is if you try with the human teachers, and then they very quickly become overloaded and effectively only focus on one way of giving feedback.
Okay, fantastic. Thank you very much, Jens. One round of applause. Okay, so now we would like to invite you to the coffee break and the poster session. So it's going to be a not super short, but kind of short break. But we have many other breaks and lunch. So we can find the coffee and tea and some snacks here downstairs behind you. Then the posters and the remaining snacks will be upstairs. If you just follow the stairs behind there, and you will find the room straight in front of you. Okay, and our volunteers will guide you anyway. So see you back around 11:20.
So welcome everyone again. I see a lot of caffeinated faces. So the afternoon session will start with Professor Silvia Tolu from Technical University of Denmark. And Silvia got her PhD degree in Granada with Eduardo Ros. And I can suggest you to check her thesis, especially if you are interested in neurorobotics or neuro-inspired AI. It will be super insightful for you. And now she is an associate professor at DTU, and she established a very well a lab at DTU, Neurorobotics Laboratory. So without going too much detail, if I'm missing some information, Silvia, feel free to complete it, and we can start your presentation. And this presentation is online. That's why Q&A session will be a bit different. If our speaker couldn't hear your questions, either I will invite you to ask here, or I will repeat your questions. So Silvia, we can start.
Yes. Hi, can you hear me? I hope so. Thanks for the introduction, Murat, and thanks for the invitation, especially to accept my online participation. Today I'm presenting you the work we do at my neurorobotics technology laboratory here in Denmark. The laboratory is at the Electrical and Photonics Engineering department, 20 kilometers north from Copenhagen, so in Kongens Lyngby. And here we have different facilities, so not only labs, but also what it's called autonomous system test arena, where we try to reproduce some of the conditions, environmental conditions, where we can test our different robots, aerial, underwater robots, or manipulators, both rigid and soft robots. So today I will present some of the works that we do. Of course, the time is limited, but you are very welcome to ask me or to reach me out and to talk about what we do with all these different robots. And the mission of the lab is to benefit society by providing cutting-edge perception action control methods that we can integrate into neuromorphic technology for achieving autonomous, collaborative, and assistive robotics. So the mission is this, and the goal is to unravel the mechanisms of the human brain in order to help experts, such as clinicians, to understand more about diseases, the brain diseases. So try to accelerate the breakthroughs in medicine, but also for roboticists to find new computing technologies or revolutionary computing technologies to advance robotics, especially collaborative autonomous robotics. So having said that, at our lab, we have these two main research lines. The first one is building and reproducing the brain-like circuits in software or in neuromorphic hardware, and then to develop collaborative autonomous systems that apply these principles of neural computation in order to sense and act in real human environments. By embodying these brain-like circuits into these agents, we want to analyze and decode the development and growth of our systems. So I started here at the Technical University of Denmark in 2015, and before that, as Murat said, I did my PhD in Granada, and from 2016, I was part of the Human Brain Project, where and also I had also another Marie Curie project called Biomodular. And within this project, what me and my group achieved was the implementation of a modular spiking cerebellum that was embedded in a novel bio-inspired control architecture. So the main goal was not to build high performance robotics directly, but rather systems that are able to adapt and learn from actual training towards improving their performance. So in this way, we make the robots more flexible and adaptable. So the main outcome of these two projects was different, distinct cerebellar microcircuits that could learn forward and inverse internal models of different robot bodies, such as humanoid robot or modular robots. For those of you who don't know what an internal model is, I can briefly explain this. So in 2008, Ito examined how a movement of a body part is controlled in the brain. And he stated that a feedback controller in the motor cortex generates a command that drives the body part. For example, if we talk about a robot, it can be a robot arm, accordingly to a desired instruction. And then this body part is captured into an internal model that is forward or inverse in the cerebellum in order to precisely perform the control of the robot arm, again, by referring to it. Of course, if we are not talking about a robot, we talk about limbs, no? So our arms or limbs. And then by continuing on this theory, it also explained that the microcircuit of the cerebellum that encodes the internal models are used to control, as I said before, the body part. And this microcircuit is reproduced along with the full structure of the cerebellum. And there are multiple of these combined together to form what it said a unit learning machine. And in 2007, Paul Reel and Dean made a very nice work to explain how the learning speed and accuracy of this unit learning machine is improved by optimizing the choice of neural centers and bases of these neural centers at the granular level of the microcircuit of the cerebellum. So now I'm not going into details, but just briefly, I can say that this microcircuit is composed of different three main layers, let's say, and one of these is the granular cell. So by improving the choice of these centers, the performance is improved. So by relying on these theories, what I did was to utilize an algorithm called LWPR, or locally weighted projection rejection algorithm, that I could substitute into this microcircuit at the granular layers in order to reproduce the theory about optimization and improvement of the learning of the cerebellum. And by after doing this, then I said, okay, now I'm ready to build a control architecture, a bio-inspired control architecture, where I can get benefits of the unit learning machine to learn the internal models of the robot, in particular any robot, because this architecture can be applied, as I will show you later in the experiments, to any robot. So in particular, the first architecture is called adaptive feedback error learning architecture, where the unit learning machine provides feed-forward corrections, and it's learning the inverse model of the robot, while the second architecture I built is called recurrent adaptive feedback error learning architecture, that is learning the forward model, and it provides so recurrent corrections in terms of sensory corrections. So before giving you the examples, I want also to talk about what are the main needs and challenges in our neurorobotics research. So there are two main research approaches. One is called exploration, and the other one is called exploitation. So in exploration, attempts to test new theories about the neural mechanisms responsible for specific behaviors in humans and general animals, while the exploitation focuses on the embodiment of cellular level models that reproduce the neural activity. Of course, these two approaches are not contradictory, but there are limitations, especially for realizing the cellular level models, because since they are computationally heavy, so we need more computational power for achieving real-time operation, and also we are lacking computationally efficient, biologically realistic neural models. And so this limitation makes the possibility of employing cellular models in the exploration theme more challenging. But there are many possibilities now, given the hardware, the neuromorphic hardware, such as the Loihi, for example, to overcome these gaps. And we are working towards this goal as well. So these two examples are showing the two experiments that we did by relying on functional AI. So where the cerebellum was not as biologically plausible as we would like, such as using spiking neural networks, but was an analog model of the cerebellum. But the goal was to test the theory about the learning of the forward and inverse internal model. And as you can see, so we used two very different robotic platforms here. One was the iCub humanoid robot, and one was a modular robot called Fable that we shaped in 4-leg configurations. So in both these examples, we wanted to test the adaptive capability of the cerebellum by learning these internal models to achieve coordinated, accurate movements and also make an online learning. But then we said, okay, this was in simulation, we tested the theory, then we wanted to embed these computational brain models into physical robots and show promising results for even more complexes, future more complexes environments for example, navigation and manipulations. So under changing scenarios and complex systems, the brain capabilities of online learners can be very beneficial because the brain can actually learn unknown dynamics, such as even the coupling terms of dynamical models of the robots. And the two works I'm showing here so relies on these cerebellar internal models and to ensure a more accurate, smoother, as you can see here, and faster tracking performance compared to traditional control methods. Another example is about sensory motor coordination. So here in this video, you can see a man performing crazy actions. So he's very well coordinated, and you may think that he have trained a lot. Yes, he has. But what maybe you are not thinking is that he has trained since he was born. And since we are born, so we deploy what is called motor bubbling, which is a random motion generation that covers the whole space and leads to the formation of sensory motor maps. So by relying on these sensory motor maps, humans can perform motion tasks in a very efficient way. And therefore, together with the robotics group in Hong Kong, we asked, can we replicate this into a robot? Yes, so we did that. We built a spiking neural network for approximating differential sensory motor maps of the universal robot arm. And the feedback data provided from proprioceptive and exteroceptive sensors, such as cameras, were encoded and fed into an input layer through this motor bubbling process. So in the experiments, we carried out a typical visual servoing task to show that the spiking neural network we developed was able to handling noisy sensory readings to get the robot arms movements in real time. And then based on this experience, as a continuation, we exploited the assumption that the cerebellum could use the internal forward model to provide anticipatory signals by learning from the error in sensory states. So what we did was to have the cerebellum learning the forward model, and we built this control architecture where the cerebellum is acting as a Smith predictor. So this Smith predictor is predicting sensory corrections and then we calculated the prediction error based on the actual sensing reading that we used to update the model itself. And then this output of the cerebellum is used to as an input to the differential mapping spiking neural network. So the cerebellum improves the servoing performance as the error decreases over time. And then we also said, okay, can we also use this knowledge and this control architecture to reproduce an experiment that is done by cerebellar ataxia patients? And we were able to do in the end to show that the spiking cerebellar model was indeed able to act to reduce the deviation from a target path. So this is an experiment called the radial reaching, where the robot, or imagine a patient with cerebellar ataxia, has to reach different point from a same central point, and the cerebellum was actually reducing the deviation from the target path and also the execution time. So in the lab we have many different open topics. Today I'm giving you two examples of among all of them. One is about human-robot interactions, and one is about the models of brain circuits for investigating healthy and unhealthy brain. So the first one, human-to-robot interaction, it's not what we are trying to do is not what you see in this picture, but having robots interacting nicely with the humans, being collaborative and kind with us. So in particular, in the lab we have a soft robot that was built by the Biorobotics Institute in Pisa. And Adrien, my PhD student, is working with it toward making a control architecture, hybrid control architecture for achieving compliance during a human-robot interaction. Why compliance? Because compliance focuses on the ability of the robot to adapt to its environment and to respond to external forces or changes. But there are challenges when we try to use especially soft robots like this, because the high accuracy for the control of soft robots requires detailed analytical models that are difficult to obtain and generalize. And then also when there are drastic variation in the models of the soft robot dynamics, because of different conditions, then we need exhaustive dataset recording and continuous online adaptation. So in order to overcome these challenges, what we are trying to do is, first of all, try to start with a non-linear model-based control design that can give some stability and robustness requirements. So during this process, what we do is, first of all, we do some data gatherings. So we take the data, as well as I showed before, by using motor bubbling. And then we build a nonlinear model. So we fit the data into a differential equation describing the dynamics of the robot. And then we define a set of terms, for example, x dot, and so on. And then we find all the coefficients for those terms by using a system identification tool. In this case, it's called Cindy. And then we build a robust controller based on this model that is called a super twisting sliding model controller. And then the control, we have this control architecture that I'm going to explain briefly here. There's not so much time, and I need to rush, sorry for this. So we have two main blocks. One block is the super twisting sliding mode control that provides robust control against disturbances, and also provides a feed-forward term, a velocity command, to cancel the known part of the dynamics. And the second block is the one having the task of finding and control actions that realize this velocity command. So we apply these control systems to by using one single robot module, where the end effector has to follow this trajectory, and the performance was pretty good. But when we attached the second module, then we realized everything crashed. And this is because, yes, the model was very well fit with the data collected with one module, but still the controller was not able to, was struggling a lot with this new change. The new configuration. So what the first attempt we have made was to substitute the super sliding twisting mode controller with a learning controller. So if we substitute the super sliding controller with a learning controller, we can make it learn the mismatch with more precision, since the algorithm we are using, and by the way, we are using the same algorithm I showed you before, the locally weighted projection regression, can learn nonlinear functions. So the nonlinear controller was finding a gain to compensate the mismatch for a given instant, but the signal the signal that we are trying to model is not it was not a function of the current states and actions. So that's why the learning controller is now, as you can see here, working better when we attach the second module. Of course, there is still margin to improve. For example, there are delays that have not been modeled. So now we are on the next step. It will be to substitute even the inversion part, this part of the control architecture, with a learned model that can account for delays, and also use a more bio-inspired architecture. So, for example, making the control architecture I showed you before, the Smith controller, also for this case with the cerebellum, then, in order to even get better performances. The last example I want to show you is about Parkinson's disease. And what we are trying to do is overcome some of the challenges about the investigation of disease, which are measuring neural circuit degeneration, building early diagnostic tools, and providing an objective symptom classification. And the solution that we have in mind is multiple. Of course, we need to start from modeling the brain, both for example, in software, but also in silico, because these models provide testbeds for repeated and controlled research. And then we are also building neuromusculoskeletal models and AI-based solutions for digital biomarkers identification. And then provide standardized protocols for data collection. Today, I'm just showing you a computational model that we have built as an initial step for example, revealing the problem of freezing a gate, which is the arrest of movement, as you can see in the video, and difficulty initiating the movement. So we have built an error architecture that can be used to understand how to alleviate cone contractions during motor impairments in Parkinson's disease. First of all, I introduce what is a central pattern generator for those of you who don't know yet. In the spinal cord, there are rhythm generating circuits that are called central pattern generators, and they are very special because they can produce oscillatory output in the absence of rhythmic input. And this video shown an experiment where the very first experiments in 1911 on the cerebrated cats, and even if the cat was decerebrated, so the spinal cord and the nerves from the hind limb muscles were cut, it was still able to walk. So this first experiment shown the existence of these central pattern generators. And normally, the common architecture suggested for the central pattern generator is a half-center oscillator, pictured here. And it consists of two populations of neurons mutually inhibiting each other. So this means that when one starts spiking, the other is inhibited and vice versa. So this creates an antiphasic output as portrayed in this plot, which leads itself well to controlling an antagonistic muscle pair, for example, biceps or triceps. How much time do I have left? Don't know. Okay, so I will just close it quickly. So what we did was to implement a very biologically plausible neural network based on these concepts, so a spiking neural network model, based on some findings from Professor Runesberg's lab here in Copenhagen University. And as you can see here, it's a huge spiking neural networks that is involving what is called rhythm generators, so half-center oscillators, and together with inhibitory populations, excitatory populations, and motor neuron population, which outputs can be connected to musculoskeletal models that we are building to reproduce the freezing of gait, for example. And since we are studying Parkinson's, so we have also developed dopamine modulation, and we have studied the both positively and negatively correlated modulations. And also we have started studying the effect of gap junctions, because we want to see the influence of membrane potential between neurons without spiking. And we hope that actually you can find this publication very soon available online. And another one is under review about the gap junctions. So we hope to find a way to explain one of the root causes of Parkinson's disease. And then you can also read this paper that talks about how to combine machine learning together with computational modeling for building tools for testing diseases, and not only. And then, of course, we are open for collaboration, because achieving embodying intelligence, artificial AI means building all together all these different blocks, that we need collaboration from different labs. And thanks to all my collaborators so far, and funding agencies, and thanks to you for listening. And yeah, if there is time for questions, thanks.
So we can start our Q&A session. And Silvia, can you confirm that you can hear me?
Not very well, actually.
Okay.
There is lots of echo.
All right. Now, who wants to ask question? Yeah. Let me take it.
I worked with neuromorphic computation before, And I was very saddened to see how that in many cases it underperforms when compared to standard techniques like Kalman filters for control, or for when comparing SNNs with regular fit for neural networks, they usually underperform. But now you give me a new insight into the neuromorphic hype, which is that we can isolate biological function in patients, let's say with Parkinson, and then we can replicate it and re-give functionality to humans if we can isolate it and then re-engineering. Now, except for that, can you tell us more insights, let's say, about why it would be worth the attention for future research on neuromorphic computation as opposed to just doing hardcore optimization and scaling on what we know already works?
Okay, thanks a lot for your question. Actually, when you say underperform, I'm not sure to agree with this, because it's actually the opposite of what I said. But it depends on the situation and on the models that we use. For about your specific question about so how we can get benefit of neuromorphic tools, it's because neuromorphic hardware, for example, allows us to implement more biologically plausible neural models, because they are actually made ad hoc for this, and then speed up the computation. So especially when we need to deal with lots of sensing information, so that is a benefit. And then, as I showed in my presentation, the neuromorphic computing is giving something that traditional methods are not giving. So the fact that you are augmenting and the learning itself, and the neural networks can then deal with changing and conditions, online changing conditions, right? So we don't need to learn before offline everything. So we just can do online computations. Have I replied to your question? I don't know.
Yes, my question was more about what can neuromorphic computation tell us, not only about brain-related problems, but also computational problems at large that are relevant for us to solve with machine learning and AI.
Okay, so what the neuromorphic computation says to us is also how to be more efficiently in terms of energy consumption, for example. So we need less resources, but at the same time provides more power, computationally speaking. And the spiking neural network is maybe, as you said, the underperformer with respect to the traditional AI. But by using this neuromorphic hardware, we can reduce the energy consumption. So it's a trade-off between accuracy and an energy consumption. And then the spiking neural networks can allow also the achievement of methods and tools that can allow explainability and transparency of neural networks. So there is a very open research. But let's see. I think nobody yet has demonstrated that, so it could be something relevant to study.
Nice, thank you.
Okay, we can have one short question, if you are willing to come here and ask. No? All right, so let's thank the speaker again, and Her PhD student is here in case you need more detailed information about the ongoing works. So please find Andrea, maybe. Okay. If you are here, just raise your hand.
Thank you.
Thank you, Sylvia. See you next time.
See you. Bye-bye.
Give me time. Do not,
Okay, so now it is my pleasure to introduce Professor Calandra. Professor Calandra has recently joined TU's Dresden as full professor. But before there, where he started his own lab, but before there, he was at Meta, where he started their very own robotics lab in Menlo Park. And even before then, he was doing a postdoc with Sergey Levin at Berkeley and a PhD with Jan Peters. Calandra is an expert in touch perception and dexterous manipulation. And I'm really eager to see all the recent work he's been doing. And I'm sure he's going to tell us a lot of interesting stuff about his work and his collaborations. So please welcome Roberto Calandra.
Okay, hello everyone. My name is Roberto, here in Calandra, sounds very strange. Thank you very much for having me here today. And it's my great pleasure to be here to talk to you about some of our work over the last years on perceiving, understanding, and interacting through touch. And the first question I want to start from is, other one. So why robots? Well, the reason why we are quite interested in robots is because overall we believe that robots can have a very beneficial impact over our society in many different fields. From replacing kid laborers in the coal mines of Thailand, well, this doesn't really show anything, all the way to help us in medicine and elder care. As we know that in our societies, the average population is growing older and older, and we will need more and more manpower to be able to sustain this type of quality of life. And if we have a look at some of the work that have been doing in robotic traditionally, this is a video from 2015 from the DARPA Challenges. These were some of the best team in the world in robotics, spending 2-3 years with team of hundreds of people and millions of dollars to basically be able to field some of the best robots in the field and to be able to navigate through some terrain and manipulate objects and drill and open valves. And what is astonishing to me is that besides having really beautiful robots, all of these robots fails in a way that no humans would ever fail. I have, 6-year-old kids at home. He would never fall down like in this way, like this robot would fail. So fundamentally, all of these robots don't have any capability of really understanding what's happening around them and really have the intelligence of adapting. And so The questions that we fundamentally am interested in trying to answer is how do we develop robots that are useful in the real world, that are useful in everyday life, and that can interact with humans in a way that is safe, that is meaningful, and that is adaptable to the needs that we have. And of course, this is a really complicated task. It's a very, sort of multifaceted problem that is going to take decades to solve. And some of the problems that we have at the moment in the fields goes all the way from hardware, from how do we build robots, all the way to how do we then control them, how do we do high-level planning. And fundamentally what I believe, and I think most of the other people that are here today believe, is that AI will play a really important role in giving us the capability of being able to generalize and put robots that are more intelligent into our houses. And some of the topics that we are working in my lab include multimodal sensing, adaptive hardware configuration, and quick adaptation to new tasks. And each one of these lines of research have led to different contribution to different subfields. But today's talk, I'll be focusing and talking only about tactile sensing. This is one of the fields in which we are probably most known at the moment. And I'll basically guide you through the last few years of what we've been doing in this field. Yeah, this is really invisible. Oh, too bad. So let's start from why do we need touch? At the moment, 99.99% of the robots that we have don't have touch. However, as a human, touch is probably the most important sense that we have into our everyday life. Every time that you are grasping an object and you are balancing with your finger, what you're doing is that you are sensing forces that are basically being exerted from your fingers onto this object, and you're trying to balancing them. Every time that you're taking a step and walking, what you're doing is with your feet is that you're sensing the force that you're extending on the floor, and you're trying to balance them. So the fact that robots that are designed to interact with the world are not capable of measuring the most important variable and value of interaction, which is forces, is fundamentally a huge flaw of what we are doing today. And from a evolutionary perspective, there are very interesting facts of how humans use touch. Touch is the first sense that evolved from an evolutionary perspective when we were small amoebas navigating into primordial soup, and we developed this idea that we can actually touch things and sense them with our cilia. And over years, vision actually comes much later from evolutionary points of view. And there are people that are born without sense of vision, that are born without sense of audio, but you cannot be born without sense of touch. It's actually impossible. There are only a couple of cases in the last 200 years of medical science of people that lost the sense of touch because basically half of their brain was blown out and they survived. So it's actually very deep into humans, the fact that we have touch and we use it in a very subconscious way without even realizing how important it is. And Roland Johansson did a lot of experiments about the physiology of touch, and this is one of the videos that I like to show. What Professor Roland Johansson did was that they would basically ask people to do very simple manipulation tasks like lighting a match, and then they would anesthetize the sense of touch of people while keeping their motor control capabilities. And suddenly, the same task that you can do very easily without even thinking about it becomes much, much harder and takes you way longer to solve. And the reason here is, of course, because humans do use touch in all of these tasks, even though you might not fully realize it consciously. And now, from an historical perspective, the reason why touch sensing is not so developed and are not so common nowadays is mostly for historical reasons. The reason is because touch is hard. Touch is intrinsically a multidisciplinary effort because it requires you to build tactile sensors. It requires you to then develop algorithms to make sense of what raw data you get out of your hardware, and then you need to include this into your control loops. And historically, people have been trying to focus only on a single one of these layers, providing their own small contribution, but have done so in a way that is not basically scalable, that is not synergetic. So, hundreds of PhD students have built amazing tactile sensors over the years, and then they finish their PhD, and the tactile sensor is just taking dust in the shelf of some of the lab. So some of the questions that we've been trying to focus on over the last few years is how can we lower the entrance bar to this field by enabling reproducibility and enabling the reusability of components that people and research that people develop in a way that is actually useful to move forward the community in an incremental way. And of course, this leads to a philosophically very simple answer, which is actually very practically hard to implement, which is that we want to have standardization. And what we would really like to have as a community is the creation of ecosystem of tools that anybody can use, can contribute to, and over time and decades, we can basically move forward the field. And this is going to be a big focus of the talk that I'm going to give you today. I'm going to show you, within the time I have, some of the examples of our contributions toward trying to build this standardized ecosystem of tools for touch sensing. And what I want you to give is also a little bit of my perspective of how I see touch in a more historical perspective compared to other sensing modalities. Because I think that we are in a very, very particular moment in time. In the 1800s, the introduction for the first time at scale of telephones enabled us, as a community, as a society, to be able, for the first time, to record audio, to be able to transfer audio long distances, and to play it back. And this led, of course, to not only significant opportunities and new capabilities for our society, commercial applications, but also led to the creation of new fields of computational science dedicated to making sense of audio as a sensing modality. Fields like signal processing, digital signal processing, natural language processing, more recently using machine learning toolbox. And this really revolutionized the way that we understand audio, we can transfer audio, we can play it back. A similar process happened in the 90s with vision through the introduction at scale of cheap, reliable cameras, digital cameras, that now we can suddenly take pictures of things, we can digitize images, we can transfer them over long distances and play them back. And again, this had huge impact on our society. Every day we now have microphones and digital cameras in virtually every device that we buy. And these things are reliable, they are cheap to produce, and this really deeply impact our life. The fact that you can just Skype and call somebody on the other part of the planet is really powerful, it's really cool. And at the same time, this led to the development of computational science, of field of science, dedicated to making sense of vision as a sensing modality. And an example in the field of machine learning is computer vision, which is an extremely successful community where they are able to do amazing things. They're able to understand images. They're able to generate new images from text. They're able to change appearances of images and videos. And what I'm here proposing is that we are in this very specific moment in time where we are at the verge of being able to produce at scale cheap and reliable tactile sensors that are able to digitize touch in a way that was not done, that was not possible before. And if we exploit this moment, this will lead to the creation of a new field of computational science dedicated to be able to make sense of touch as a sensing modality, and will enable us for the first time at scale to be able to digitize touch, transfer it over long distances, and play it back on the other side of the planet. And so this is the historical perspective that I want you to think about while I show you all of the work that we are doing toward this goal. And in order to reach this goal of digitizing touch, we've basically been thinking about what are the pillars that we need to develop in order to be able to do this. And some of the pillars that we've been working on include hardware, touch processing, simulation, benchmark and datasets. And we've also been very active in application and in trying to grow the community. We've been organizing a lot of workshops, and I will not have time to talk about all of these pillars, but I want you to at least know that there are many pillars that we are working on. And the one that I'll be focusing today are going to be hardware, touch processing, and some applications. So let's start from hardware. The type of technology that we are quite fond of when it comes to tactile sensing are so-called vision-based tactile sensors. There are many technologies that have been developed over the years. All of them have different pros and cons, but the one that we choose to work with is vision-based. The idea of vision-based is very simple conceptually. You basically have a piece of silicon. You have structured light that get projected onto this piece of silicon. And whenever this piece of silicon is going to deform, this is going to create changes in color or shadows from the reflected light. And this is captured then from a camera that basically just record these changes and digitize them. And this is a really nice technology because it allows you to have basically no moving part. You don't have any electronic that is moving, which allow us to make sensors that are high resolution, cheap, and reliable. And in practice, this technology was invented many times over the years. It was first introduced in '63, then reinvented in the '80s, then reinvented again in 2000. And most recently, Ted Edelson from MIT is one of the persons that helped to repopularize this technology. And our small contribution in this field has been the design and open sourcing of a sensor that we call DIGIT. DIGIT was designed to be the first mass-producible, low-cost, high-resolution vision-based tactile sensor with the idea that we wanted to build a sensor that can be used to democratize touch, a sensor that you can 3D print in your at home if you have a 3D printer, a sensor that can be produced at scale at high quantities, low cost, and that is reliable. And the sensor is open source, so if you are interested, you can actually go out there and produce it. And the type of tactile readings that you will get are something that look like this. And I would like to point you, for example, to the example here of the Velcro. This is a piece of Velcro, and here at the bottom you can see a reading out of the DIGIT, where you basically can see the geometry of what you are touching. You can see the individual teeth of the Velcro down to a resolution of about 20 to 50 micron, which is roughly compared to the resolution of a human fingertip. And now this sensor, this is really cool because we can basically capture geometry of what you're touching, and through the use of algorithms, we can also estimate normal and shear forces, which is pretty much 90% of what we need to be able to sense touch and digitize touch and use it for robotic applications. Now, just to give you some perspective of what was the state of tactile sensing before DIGIT, the leading competitor, commercial competitor at the time was Biotech, which was a sensor which had 3 orders of magnitude less taxels, so lower resolution, and it had a cost that was about 3 orders of magnitude higher than what it costs to make a DIGIT sensor. And both of them can be integrated into multi-finger hand. Our DIGIT sensor is a bit bigger than Biotech, but it's still 2 centimeters by 2 centimeters. You can put it on a robotic hand. And I'm happy if you want to see it. Please bring it back. My lab needs it. Yeah. And moreover, you can just go and build your own DIGIT. Now, in addition to open sourcing the sensor, We also partnered in 2021 with a startup, and we gifted them the right to be able to manufacture these sensors and sell it, which means that if you have a little bit more money and you don't want to 3D print your own sensor, you can actually go online and buy it from this startup. This, of course, means that suddenly becomes a lot easier to have access to tactile sensors. And since then, Digit has become the most widely used tactile sensor in robotics, with thousands of digits being used from researchers around the world. And also several companies that have shown interest in integrating Digit into industrial application. An example is Mitsubishi that integrated Digit last year. Now, as I said before, Digit was designed with the idea of being a cheap sensor with a very specific form factor that wanted to democratize touch. However, this is not the only form factor that we can build vision-based tactile sensors. And over the years, we have also explored many other different types of form factors for our vision-based tactile sensors. This is the OmniTac, which is, for example, designed to be more similar to a human thumb. So omnidirectional, you can now sense from all the directions. Recently, we designed and open source another sensor called EVTAC, which has the nice property of being using an event-based camera, so that we can have much higher spatial resolutions in the order of kilohertz. So this means that we can also sense vibrations very nicely. And one sensor that we open sourced just last week is our Digit Pinky, which is the next generation of Digit, which is roughly the size of a human pinky with a diameter of 1.3 centimeters. And what is really cool about this sensor is that it's actually so small that we can use it for medical applications. And one of the applications where we have a proof of concept is to being able to touch prostate tissue and be able to identify where cancer is. Now, this is, of course, a proof of concept. It's not a medical study, but it really showcases, in my opinion, the potential for this type of tactile sensors, and more generally, the potential for touch in applications that go also beyond robotics. And this work was done in collaboration with a number of other institutes, including the Stanford, Facebook, where I used to work, and the National Cancer Tumor Research Institute of TU Dresden. Now, in the moment when we now have hardware which is getting to the point of being reliable, cheap, good enough for applications, how do we make sense of these informations? How do we make sense of these images or videos of touch? And fundamentally, there is extremely limited literature on how to process informations. We know that we would like to use machine learning because these are very complicated type of inputs. They are very rich, they're very high dimensional. So using analytical tools is very hard. But using machine learning, there is not so much understanding. There is not the same level of maturity of, let's say, computer vision that has 30 years of understanding of what are the right computational structure, what are the right inductive biases, and so on. And so our idea is that we want to build a new field of computational science, which we call touch processing, with the idea that over the next decades, we want to be able to answer all of these questions. What is the right inductive biases to make sense of touch? What are the right type of representations? What is the equivalent of a convolutional neural network for touch that can integrate both over space and time? And as a very small contribution toward this creation of a new field of computational science, we have open sourced the first machine learning library dedicated to touch processing, which we call PyTouch. And the idea is that we want to try to engage with the community toward building a tool that is easy to use, where you can just download pre-trained models and directly use it in conjunction with Digit sensors or any other sensor you have. And you can ideally also benchmark and compare against other algorithms. a little bit in the same way that OpenCV used to be for many years in the field of computer vision. Now, this tool, we also, of course, use it for research. And some of the questions that we have started to answer in the field of touch processing include questions about what type of representation do we need? What type of features can we learn with touch? And some of the sort of first discoveries that we've made is that we can already demonstrate transfer across different sensors. There seems to be some feature of touchiness, which is independent from the specific sensor that you use. And at the same time, there seems to be transfer across different tasks. So you can learn features in a task-agnostic manner and then transfer it to different tasks, and these features are still being useful, which is one of the really cool things, for example, about CNN and first discoveries in deep learning. Recently, we also published a paper on starting to integrate also language together with touch, where the idea is that we would like to be able to touch something and say, okay, this feels soft, this feels hard, this feels rough, smooth, and so on. And so integrating more and more sensing modalities in large language models, or vice versa, integrating large language models in other type of sensing modality, I think it's a really interesting future direction of work. Now, after hardware and after touch processing, what I want to tell you next is a little bit some of the applications in which we are working. Now, in my mind, there are many different applications where touch could be useful. Of course, medical applications are really, really important. Medical robotics, but also amputees. If we are able to digitize touch, we can now have the hope to be able to restore the sense of touch to people that have lost their limbs. In the same way, metaverse, if we can now digitize touch, we can also likely be able to improve the reproducibility of touch into haptic devices to feel a virtual world, to be able to touch your grandparents, your grandmother over the metaverse. E-commerce. I would like to be able to take my tactile sensor, touch a sweater or a shirt and say, hey, Alexa, buy me a sweater with the same material or with the same texture or with the same thread or that feels like my favorite sweater. And finally, robotics. Being able to manipulate objects, be able to grasp things that are fragile and that require you to really understand what's going on. Over the years, we've been working on many different aspects of robotic manipulation, from being able to identify objects from touch to 3D reconstruction and learning to play piano in simulation, which I think is a really cool application. But some of the ones that I'm mostly fond of include learning how to grasp. This is a work that we did when I was at Berkeley. And the idea here is that we want to be able to learn how to grasp everyday objects. And what we did in this paper is that we basically hoarded a 7-Eleven at the corner of the campus, and we bought every single object that was mechanically compatible with our gripper and that costed less than $10. And then we hoarded all the desks of our colleagues in the floor, and we borrowed everyday objects from their desk. And once we had this large data set of over 60 objects, we basically had the robot trying to learn how to grasp this object on their own, self-supervised manner, completely autonomously for over 2 weeks. And the result was a system that was now able to generalize to unseen object and be able to learn how to grasp and how to re-grasp if the initial configuration was not good, until they find a stable position that feels, from a tactile point of view, the right place to grasp the object, and then they could lift it. And the result was a system that had about 83% of success rate compared to a system that, if only using vision, was significantly worse in performance. Another cool paper that we did was to use Digit to be able to manipulate glass marbles between 2 fingers. with the idea that we want, this is actually a really hard task for a robot, because if you apply too much force, you will squeeze the marble out of your finger. If you apply too little, you will basically lose it to gravity. And so be able to manipulate marbles to a specific position in your fingertip is something that we did, and using model-based reinforcement learning, we were able to solve quite successfully. Overall, the goal that I would like to reach is to be able to achieve the same type of general purpose manipulation that our hands have, where we can basically do amazing things. I can not do half of these things. I mean, some of these are really, really complex. Toward this goal, last year we also presented a new paper. I don't know why the video is not working, but this is a paper where we are able to learn how to rotate objects in hand, objects that, again, have never been seen before, so this is all generalization. This is using tactile sensing, and we have proofs that using tactile sensing help compare, again, only using vision. So this is to further support the need that we do need tactile sensors. And if you were at NeurIPS, this work was actually presented also in the robot learning workshop. It was presented at the Facebook booth, and it also won the Best Demo Award at the workshop. Pretty cool work. Now, beyond being able to manipulate objects, what we do as humans is also that we are able to reconstruct the shape of the object as we manipulate it. And we are also able to identify, if you close your eye, you are able to identify where your fingers are with respect to an object, to the pose of the object. And this is something that we started exploring in these papers that we also published a few months ago. Now, to conclude, all of this work would have not been possible without hundreds of collaborators that I had over the years. I'm very grateful and thankful for all of them. They're amazing people. At Facebook, we had a team of about 30 people. Some of the best engineers I've worked with in my life, doing all the things from mechanical engineering, optical. We were working with people that build the Hubble telescope, to how do we cast silicon, how do manufacture these things. And I'm deeply grateful for having worked with all of the people you see here and many more that couldn't fit in this slide. To conclude, the message that I wanted to convey today is the fact that touch sensing is a key sensing modality both in humans and in robots. And I believe that this sensing modality will play a really important role in robotics specifically, but also more widely into commercial application in our society. And toward this goal, we've been starting to build an ecosystem to be able to simplify the life of researchers that want to approach this field, that want to do research in this field. And some of our contribution include hardware that is cheap, that can be bought from people, simulators that are fast, that can be run at hundreds of hertz, and touch processing tools where we can start to explore fundamental questions about the nature of touch as a sensing modality and what are the right machine learning algorithms to be able to do so. And in the long term, what we want to do is that we really want to do touch sensing practical in the real world. Ideally, I would like 5 years from now to see every single robot build to be provided with touch sensors that are actually used to improve their manipulation capabilities. And I believe that from a historical standpoint, we are in this very rare and special moment where we are at the verge of this digital revolution of touch, where we will be able to digitize touch like has never been done before. And so my suggestion, if you are a master's student, is this is a good field to be working on in the next few years. Okay, thank you very much, and thank you again for having me here today.
Thank you for your presentation. So I had one question. We also have a lot of tactile sensors that have been developed in the sense of like capacitive or just pressure sensors like piezoelectric.
Yep.
Could we somehow, and we get a lot more information from your vision-based tactile sensors, could we use the vision-based sensors to sort of extract more information from your basic piezoelectric or capacitive sensors, because they would be much more like compact, and then probably that could be developed into more direct tactile sensing technology probably?
Yes, I think this is a wonderful question. This is something that we have been hypothesizing for years. So my hypothesis is that touch sensing is particularly important during learning because it gives you features and representation of forces that you cannot learn otherwise. But in principle, if you learn this representation, it's very likely, as you mentioned, that you can then use inferior tactile sensing technology, less resolution. Maybe you don't even need a tactile sensor at all, as long as you have the right representation that something like forces exist in the first place. As a human, all the video that I showed you from Ronald Johansson, what they really show is the fact that humans use touch in the controllers that they have, but if you keep them play for long enough without touch, they will eventually be able to solve the task, right? So there are good chances that, if you remove touch or decrease the quality, you can still do a lot more than if you did not have touch in the first place. Yeah.
Thank you.
Should I go? Yeah. Okay, so I wonder whether you folks considered just hook up an event camera, right? Like, with digit. And then therefore, instead of doing, let's say, frame-based sensing, you just do event sensing.
Yeah. Yes, this is what EVTAC does. This sensor is event-based. The advantage of event-based is that, of course, we can pump up the temporal resolution. We can now go from a standard camera like the Digit uses. The camera that we use in Digit is a cell phone camera that costs 50 cents, again, for being cheap and being mass-producible. This event-based camera that we use in this paper costs 5,000 euro. So it's great for science. Now, can you put this type of product on the market? Well, not so many people would buy it, as you can understand. On the other side, it does allow us to start exploring, what more can we sense if we have high resolutions. And with this sensor, we can actually feel vibrations up to about 500 hertz. And vibrations are very strong hints, for example, of incipient sleep. So there is value in having this type of exploration. On the other side, we also don't have right now the machine learning tools to process efficiently this type of event-based input. So I think this is going to be something that will take many years to develop. Yeah.
Yeah, I had another question. Thank you for the great talk, first of all. I think you've shown sensors with very small patches that are actually tactile or like sensitive, right? Do you think it's something meaningful or necessary to cover like larger parts of robots' bodies, and or how would you do that with these optical sensors?
Yes, this is a very good question. The answer to your first question, is it necessary? My answer would be yes. Even in a hand, in this moment we have these fingertips that are super high resolution, can mimic the resolution of a human finger. But a lot of the manipulation that we do in our everyday life is actually not with fingertip. It's with the palm, it's with the other part of the finger. So I generally would believe that having an artificial skin that covered the whole kinematic structure of your robot would be valuable. At the same time, we do know from neuroscience that the resolution that we have in the fingertip and in our lips is much higher than the resolution that we have, for example, in the back of our, in our back. It goes from 50 micron to a couple of centimeters. So do we need high-resolution tactile sensors everywhere in the schematic structure? The answer is probably no, or at least not initially. However, vision-based tactile sensor, in my personal opinion, are not at the moment the right tool to be able to manufacture this large type of artificial skin. I think that there are better technology. And the main reason boils down to the fact that vision-based tactile sensor, because you're using a camera, require a depth, let's say a technical depth, because of the focusing distance of the camera. So, in this sensor, we need about 1.3 centimeters. That is basically just depth due to the fact that we have a camera in there. And 1.3 centimeters is still very thick as a skin. It might be good for other reasons, but ideally you would like to have an artificial skin which is a millimeters or two if you really want to be able to integrate it easily. So yes, we do need skin, and no, this is not the right technology. So I would love to see more hybrid technology. And I think that if we look down the line 20 years, I'm not arguing that vision-based tactile sensor will be the right technology. What I'm arguing is that right now, if you want a fingertip, this is the right technology. Yeah, question here. I think there were.
That you have talked about how they light up the humans, and so that if they don't have touch, they get way worse with it. So I was really interested if you can elaborate how important touch is in understanding the world and actually doing useful tasks, and how precise it has to be, because let's say if they lose entirely sense of touch, they get really worse. What happens if they have it slightly worse, and how precise the touch must be for the robots?
The answer I'll give is very unsatisfying in the sense that I don't have answer to most of these questions. I don't have an answer of what is the right resolution that we need. It's something that we are studying. We have hints that we definitely don't need the resolution, at least for the type of task that we're currently doing, like grasping. You don't need the resolution of this type of sensors. You're more somewhere like half of this. But it's task dependent. So you might not need resolution for grasping, but then you need a lot of resolution for incipient slip, because you need to be able to really measure very small forces. You need to really be able to see how the deformation of the material is. So this is to be known. Also quantifying how important is touch. We have extremely limited work that quantify performance of touch versus performance of vision. I only know two works, because we did them, which is the grasping one, where we say, okay, what happens if we train another model with the same data without touch? How much do we lose? And we have there some quantities, about 15%.
It's like how impactful is the smell of something, right, to perform a useful task?
The answer is that I don't know, and I would love if somebody in this room would actually do this study, so that we can go to everybody else and say, hey, look, you need a tactile sensor because this improved by 10%.
Yeah. Because then every robot would require some tactile sensors because they improve them. Yeah, it's really interesting. Thank you.
On the other side, I can tell you that anecdotally, as a human, you can do a lot of things without vision. You wake up in the middle of the night, you need to find your phone. You're not going to switch on the light. You're just going to go and taste until you find it. Or if you're searching for a scissor inside a drawer, you can just open it, search until you find, oh, this is the scissor, this is the right shape, this is the right material. So you can do a lot.
Yeah. Thank you.
So congratulations on building this beautiful sensor, and thank you for making it open source. As applications for touch, you mentioned metaverse or e-commerce, but those would probably require actuators rather than sensors. And existing tactile sensors tend to be rather bulky and low resolution. What do you think is the most promising actuation principle to build a tactile actuator, tactile display?
So for the e-commerce, I don't necessarily think it's necessary, but I can discuss this offline.
Okay.
For the metaverse, you are right that if we want to play back the sense of touch, we do need a proper haptic render device. This is outside of my work. I know many people that work on this, and from what I personally have seen, I think we are still many decades away from something that is satisfying in reproducing touch, but I think that eventually we will get there. And there are smarter people working on this than I am. So I don't plan to work on that.
Hello. Hi. Okay. Thank you for the talk, and it was very insightful. I have a question. Like, as you said, the touch is all about estimating the force and balancing out. So why don't we use a force sensor instead of touch, and then train a physics-informed neural network so that it can balance the object or the given object? So what's your view on that?
There are a few reasons. One reason is very practical, which is that fork torque sensors are typically bulky and expensive. If you want to buy a good fork torque sensor, it's probably about 10,000 euro, and probably the size of a small tennis ball, right? The other reason is because fork torque sensors can be very accurate in giving you the information about the force that is being applied, but what you're missing is the information of where this force is being applied. So if you imagine that you have a fork torque sensor in your elbow, for example, but then you can be touched in many different places. Potentially, you can even be touched by many different forces in different places. You are losing this information of where the touch is happening. And there is work, for example, from Andrea Del Prete, who used to be at IIT, that showed that for balancing of humanoid robot, if you cannot know exactly down to a couple of centimeter or so where the force is being applied, this can lead to catastrophic consequences because you cannot really estimate what's the right torque being applied and things like this. So skin or tactile sensing is cool because it gives you both the where and the how much.
Okay, well, another applause for Roberto. Okay, so now, if you please, we are happy to provide a very, very nice and tasty free lunch upstairs. I cannot repeat it too loudly and too often that it's free because there are too many students around in this building who might come and steal your food. But if you move upstairs in the same room as the poster session, you will find the buffet, and there should be some really good menu we chose for you. And then we're gonna see you again at around 2:20, okay? Thanks. Okay. Welcome back, everybody. I hope that you enjoyed our complimentary lunch. Don't worry, more snacks are coming. Even at the end of the day, all the drinks are going to be aperitif and even more snacks. Okay, so it is my pleasure to welcome our next speaker, Guido De Kroon. He's a professor at TU Delft since 3 years, right? It was quite, quite a while now. Last time we met, it was a bit longer ago. Okay, anyway, so he's doing some really impressive work on aerial robotics and has recently been awarded a lot of very prestigious grants, including an NWO-VICI, which for the non-Dutch is kind of equivalent to an ERC consolidator grant. And we also got recently awarded a very large cooperative grant together between Tilburg University and Delft on swarms of drones. So it is our great pleasure to have him as a guest today, and we are really looking forward to listening to his speak.
Thank you, Giacomo, for inviting me, and really looking forward to also working more together. And so I found out today that Tilburg is pretty close, actually. It's pretty short from The Hague if you go to the right train station. So anyway, so I'm going to talk about tiny autonomous drones and neuromorphic AI to make them fly by themselves. And most people, when they think about autonomous drones, they think about the kind of drone that you will see taking off right now. It's a quad rotor, so it has 4 propellers. And this drone is flying by itself and doing an autonomous drone race. It's actually the World Championship that happened in 2019. And this was our drone that actually got the fastest time, winning us quite a nice money prize at that. But in our lab, we work also really on very different types of drones. And the drone that you see flying into the screen right now, we have to wait a little bit because it's like slow motion. But here it is. It's the Delphi. It's a flapping wing drone that flies by flapping the wings. And it's very agile, so we were even able to mimic escape maneuvers of fruit flies. Try to swat one. They're very fast. They evade your hand. And the special thing about our design was that it could steer by changing the dynamics of the wings, and that's why it was so fast. And it even provided us with some new insights into how fruit flies make these maneuvers. Now, when you talk about autonomy of drones, then the most important topic is size, weight, and power. Because all robots are limited in what they can take on board. But if you think of drones, they have to lift everything into the air. So the computing, the sensing, and they have to be really autonomous, do all the processing on board. Now, if you look at the drone that the organizers made for the drone race, it's a pretty big drone. So it's like roughly 3 kilos and uses roughly 600 watts to fly. So that's quite some energy. But it has a really nice computing unit. That's also why it became so big, the NVIDIA Jetson Xavier. If you look at the Delphi, it's a very different kind of vehicle. So it's 29 grams and it uses 6 watts to fly. So that's much less. And typically what we have on board is a little microcontroller, an STM32F4, which has 168 megahertz processor and 192 kilobytes of memory. So that is extremely little compared to the 42 gigabytes here. Of course, I'm old enough to still have played with the Commodore 64, so I'm thinking, hey, that's 3 times as much, right? But anyway, so how can we make this thing that is 100 times lighter, how can we make it still autonomous? Is that possible? Now, one thing that roboticists typically do is for navigation, they use simultaneous localization and mapping. And they base that on making a map of the environment. And if you talk about visual SLAM, then typically this means you have a camera and you build a 3D map which is highly detailed and takes hundreds to thousands of megabytes, even for relatively modest spaces. Now you can see that we have 192 kilobytes, so we're not able to support this kind of very accurate and nice algorithm. The other avenue to intelligence is to use deep nets. And this is also something that's a bit problematic for us because if you look at an embedded unit, the NVIDIA Jetson TX2 here, so it's a little bit older, but it weighs 85 grams and takes 7.5 watts. So you can see it's 3 times as heavy roughly as the Delphi. So basically it cannot carry it. But also I think the power budget, if you use more energy to think than to fly, that ain't gonna fly, basically. So that's a bit depressing, right? So we have the 2 main approaches. We cannot use them. So what do we do? Is it possible, actually, to make these tiny autonomous drones? And I think that you will realize that this is possible. Because if you look around you, especially in the summer, you see all these flying insects. So I get annoyed also by these fruit flies in my kitchen, but okay. They're also marvelous creatures, right? So this is a honeybee. It's able to land on a flower, moving in the wind. It constructs its own base station, and it does that together with others. It can navigate over tens of kilometers and come back home. I think that's really fantastic. It's something we lack. They also communicate together. So if they find a very nice flower field, they get back into the nest, the hive. And I think the very cool thing is, so in the hive it's dark, and they do this dance. So they communicate via dance. That's nice. And so they wiggle. The very cool thing is, so it's like a code language, but in the hive they have the direction of gravity. And the angle of the dance with respect to gravity is information on the angle that the other bee should follow with respect to the sun. And so, I think it's very cool that they do that. So they work together. Oh, that's the wrong direction. they also take group decisions, so swarm decisions. Like if there's a new queen, then the old queen has to move out. So with my children, I hope it's going to go the other way around. But you know, for the bees, so the old queen has to move out, and then they send scouts and they find these different locations and they look how good is this location, and then they will advertise it with the waggle dance. And but sometimes they also disagree. There may be two places that are very similar, and then you have bees advertising these two places. And in an artificial system, this could lead to a deadlock. But what do honeybees do? If they're very enthusiastic about place A and they see a honeybee advertising place B, then they give that bee headbutts. So they're giving headbutts to disturb the dance, and then scientists prove that it always collapses to one choice. And so that's really, I think, fantastic as well. And they can recognize complex visual patterns. And all of this with only 1 million neurons. And I think that's amazing. Just to put it in perspective, we have 86 billion neurons in our brains. And so, yeah, really amazing. And I just want to know how they do that. If you think about it, so I've been working a lot on insect-inspired artificial intelligence. I think it's AI. I think they are intelligent. And this is a definition by Luc Steels of AI. It's the pursuit of intelligent behavior by artificial methods. I think that also applies if you think of the intelligence of insects. On the one hand, I think that this can really bring capabilities for our robots that we don't have yet, for flying robots, for example. But I also think that studying these robots can give us actually a lot of insights into insect intelligence. And one example is a study we had in Nature a few years back, where we showed how insects, but also drones, can estimate the direction of gravity without accelerometers. Because insects do not have that sense. They don't have the sense of acceleration. And I think as well that, if we learn about insect intelligence, these creatures, like I tried to explain, they're fully intelligent creatures. Of course, more limited than we are, admittedly. Although I cannot fly, by the way, but okay. But it's a very nice model system to learn about intelligence in general. Okay, so one of the key properties of insect intelligence is that it's parsimonious. So it's very efficient and robust. And this is in multiple aspects. So let's see if this works. Yeah, it's in the body, for example, the embodiment. So we see a flapping wing there. It's flying in a greenhouse, and it's one of the coolest demos I ever saw. It's a flapper drone. It's a spin-off from our lab. And as you see, it's flying into the wires and the plants, but it doesn't fall, and it just flies away in the end. And this is thanks to its soft body. And if you do this with a quadrotor, it will just catch with the propellers one of the wires and fall. But this flapper drone can just continue. So actually, this allows it to be less intelligent, less accurate about obstacle avoidance. Like I said, insects work together, but we can also exploit it for robots. So this swarm of drones is exploring an unknown space, and they have gas sensors. So this one is now smelling gas, and then they use a particle swarm optimization, where the robots are the particles, to find the gas source. All of this with only onboard resources. And finally, animals and insects as well use sensory motor coordination. So the drone you see, it uses optical flow for obstacle detection, but it moves on purpose up and down to induce translational flow, which makes its task very much easier. And so the use of actions, swarming, embodiment, it all contributes to the efficiency of this type of intelligence. And although we don't like to admit, we actually do the same things as humans as well. Okay. So when you see this work, we're actually using the STM. The STM is very nice because the video I show here is about the exploration of unknown environments with a swarm of tiny drones. And what they do is actually they have this little finite state machine that you see on the right of the slide. And they have very simple behaviors like move forward, follow wall, move away, rotate to the desired direction. And just by alternating and switching between these very simple behaviors, they can perform a task that's super complex. And so this is, I think, very interesting. But from experience, the limitation of this approach lies in the processing of high-dimensional sensory data. Because then a microcontroller is not super suited. You need parallel processing of high-dimensional data, and that's why we've been investing a lot of time in neuromorphic sensing and processing. So what is that? So I think most of you actually know, but okay, let me introduce it a little bit. So on the neuromorphic sensing and processing mimics animal sparse and asynchronous sensing and processing. And because of this, it's extremely energy efficient and fast. Now to illustrate, we have images here from a normal camera on the left that at 30 Hertz, and it's filming a spinning propeller. When we slow the images down, you see that it sometimes doesn't even see the propeller because it's so extremely blurry. On the right, I show a neuromorphic camera. And these cameras don't make images, but each pixel looks, am I becoming darker or brighter? And when that happens, then they send a signal. So darker is the red pixels over there, and brighter is the green pixels. And as you can see, it can perfectly follow the propeller over time. And so these events can be a microsecond apart, so they can see very quick motion, actually. Now, these inputs, they fit very well with a new kind of processor, a neuromorphic processor, in which you can implement spiking neural networks that mimic the property of neurons in our brain that most information is sent via pulses, via more or less binary pulses, actually, over time. And because of this, these can also be much more efficient than normal processors. So let me illustrate that with this figure. So on the top, there's a traditional ANN that you would run in a GPU, and on the bottom, there's a spiking neural network. So the traditional ANN has synchronous transmissions. So you have all the inputs, and then the whole first layer, second layer, etc. And actually you do that in one time step. But in a neuromorphic processor, this information transmission is asynchronous. Something happens somewhere in your visual field, this event, then it gets propagated from that neuron to the next neuron. And the others don't do anything. So if there's no information to be sent, nothing happens. And so that's very different. This is quicker. On top, you have floating point values that are continuous and differentiable. And on the bottom, you have purely discrete spikes, so binary, and it's not differentiable. And this means, it goes into the discussion that was here earlier today, so it's of course easier with the floating points to represent a lot of information, and the learning is easier. We all know backprop, so that's much easier with the network on top. And that's why the accuracy of these networks is still better than the spiking nets. Now, and finally, you have dense multiplications and additions on the top, so all neurons are active. And on the bottom, you have sparse additions. And to illustrate why the bottom option of spiking neural network is going to be faster and more energy efficient, I'm going to involve you as an audience into a very immersive, interactive part of this talk. And so I'm going to ask you a question. It's a calculation. And if you have the answer, please raise your hand. Yeah, so are you ready? Yeah, you're all pumped. I hear that. Yeah, great. No computers. So what is 6.43 times 3.22 plus 7.88 times 1.26? Anyone? I read, okay. Tell us. 30? 38? That's pretty. Yeah, it's pretty quick, accurate. But I also want the digits after the. Okay, this can take a while. I don't know. How are we on time, Giacomo? Okay, I'm going to give the answer. Very good. Very close already. 30.6334, and indeed I used the calculator for this. Okay, you're warmed up. And now I will give you the kind of calculation that the spiking net needs to do. Are you ready? So raise your hand. So how much is 8 plus 12? Okay, very good. You're all very smart. I hope now the answer on the slide is correct as well, because I think it's correct, right? Yeah. So that's much quicker, of course. Yeah, I didn't use the calculator for this. No. Anyway, so you can see that also for us humans, it's of course easier to do these kind of calculations, but also in electronics, this is the case. So what is the state of SNN at the moment? We can do backpropagation now, with surrogate backpropagation, where they actually pretend that the spike function is a smooth one that they differentiate. That works quite well. And the training is still harder though, because each neuron in a spiking network is like a little dynamical system. And this is much harder to train, basically. The accuracy on most tasks is less. Also because the information is binary, so yeah, and the training is harder, but it's faster and more energy efficient. So that's the state of the art right now. As roboticists, we also wonder, like we heard earlier today a talk also mentioning the Intel OE, and I will still show to you also in my presentation. So we have this more difficult training, but we also have quite immature hardware. So the event-based sensors now are quite available, although still expensive, like was mentioned earlier as well. But the processors are very hard to get, difficult to use, little documentation. It's almost still a research prototype, basically. So, and these chips have very limited network sizes. So, in the interest of time, I wanted to spare you the whole journey that I made, or like Odyssey, for the past 8 years, because it was my dream to make a fully neuromorphic vision and control for autonomously flying drone. And we did many steps, and we stumbled a lot of times and fell, and then we got up again. And last year we actually succeeded, this thing on a drone. So what does it look like? We have an event-based camera, and then we have this sensory data going into the Intel OE chip. It's a neuromorphic processor. And there's one spiking neural network that then goes to low-level commands for the autonomous drone. And what is it doing? So it's doing ego motion control. It's one of the first things that, as an animal or robot you would like to do, is to move to where you want to move. And it's doing that on the basis of vision. So let's look into the brain for a second. So on the left, you see these red and green pixels. You remember them from the event cam. So we have a drone that looks down. It looks at the floor, and it's looking like, okay, if you move like this, then the ground seems to pass by like that, right? So that's the kind of thing that it's trying to interpret. And then it goes into the spiking net, and you see these white pixels are spiking neurons. And then it goes here to the next layer, next layer, next layer, and that goes into the control. And so, it's quite challenging to make a single spiking net to do that. And I want to, talk a little bit about how we did it at a higher abstraction level. And so, how do you train it, right? So, and I think that one thing people may think about is, let's do end-to-end reinforcement learning. Now, of course, this is a great topic and thing to do, but in this case, it's a bit hard because event-based sensors, cameras, are hard to simulate. Actually, they simulate them by making many images. And if you already have a pretty sample inefficient reinforcement learning where you need thousands of runs to learn ego motion control with vision, this becomes much worse if you need to, simulate vision at 1,000 hertz in simulation. And so this is much too time-taking to do. So we took a different path. And the path we took is to split vision and control. So how did we do that? We first used self-supervised learning to take the vision inputs. So if we're looking at this beautiful carpet, then we get these event inputs. And then we have one spiking net trained in a self-supervised way to output the optical flow that's in these events. And then we have another network, another spiking net. We have a simulator, we have the drone there. If we know the drone motion, which we do in the simulator, then we can predict what the ego motion and the optical flow will be. So we can basically model what would come out of the first network if it works well. And we enter that flow into the second spiking net that learns with evolutionary learning, so evolutionary robotics, how to fly. Now, and then there's two things. So one thing I will present is on how the self-supervised learning works, but we also need to merge these spiking nets. That was another challenge. So the self-supervised learning looks like this. If you have your camera and you move it and you accumulate the events over time, you get this kind of blurry output on the top. If you know the optical flow perfectly, then you can take each event and drag it back to where it came from. So if you do optical flow well, you can get this really sharp, de-blurred event window. In the beginning, this network doesn't work so well yet, so it makes mistakes. This is not as de-blurred as you would like, but then you can do backpropagation to teach your network to actually de-blur better and better over time, and at the end it's able to do optical flow. And it does so without any ground truth. So you don't need ground truth, but we also don't have a reality gap, because we take the camera from our drone, we fly it, and then it learns optical flow, and that's it. This is what the hardware setup looks like. So we have a drone here, we have an event camera and the Loihi. Unfortunately, we could not connect them directly to each other, and we needed to use an upboard just for communication. And so the drone is still pretty big. So we're now working, on smaller prototypes. And I want to show you a video, so I'm only going to show one. I hope it starts automatically. Yeah. And this is the landing experiments, but it's controlling all its axes. You see the events here and the spikes. And you see that it's doing a landing, and we call it constant divergence landing. It's what honeybees do to land. And here we're playing with it. It never saw this in training, like flickering the light. Works. In the dark, also works. So when it's quite dark, the event cam has a much higher dynamic range. It still works. If you make it really dark, it crashes. So that didn't work. But that's the same, with touch. But if you fall, then touch is not enough. I mean, you feel that you crashed. Anyway. So, very important. Can we now actually see these advantages that people promise about neuromorphic, right? So this is a big table, but I make it simpler. So on top we have the Loihi. And we see that for inference of the network, it uses 7 milliwatts. And on the bottom is a Jetson Nano, and it uses 1.9 watts. The Nano runs at 25 hertz, and the Loihi runs at 274 hertz. This really depends on the sequence. So if there's a lot of events, it's 274 hertz. If it's moving slower or there's less texture, it's running at 1600 hertz. And so, very fast. And so, yes, energy efficient, yes, very fast. I don't know if I made it much too short. Normally I'm much too long, but... Okay, good, then we have more time for questions. So, the conclusion. I think that neuromorphic sensing and processing is very promising for tiny drones, but I also think for bigger robots in the end, because in the end you want to do many tasks with humanoid robots as well, and then it's still processing has to be efficient. In the future, we want to improve the learning mechanisms, so we're very actively working on online learning, so learning while the drone is flying. And we're working on increasingly complex tasks. So one thing I really want to tackle is vision-based navigation. And so these honeybees that fly kilometers and come back, I want to do the same with our drones. And with that, I want to thank the team behind the neuromorphic. It was a pretty big team. And all the other people, non-exhaustive list of other people that worked on the other studies that I showed. So I thank you for your attention, and gladly take questions.
Hello, thank you for your talk, very interesting. I have a question about the training. You say you used this approximation to the spikes to make them continuous, so that you can use, I guess, backpropagation. But have you explored other ways more bioplausible, like, I don't know if you have heard maybe STDP and other learning rules?
Yeah, definitely. So indeed, that's what we used for the self-supervised learning here. One study that we did actually earlier in 2000, was published in 2019. I think it's an interesting one. We used unsupervised learning with a local learning rule. So it was spike time dependent plasticity, but we introduced our own version of it to make it stable. And so What it did was it got these events, and then it had a first neural layer that was a convolutional layer, and we had different channels, and each channel was also competing with each other. So there was a winner takes all. And if you do that, then each channel layer learns different features, and you got like vertical edges, horizontal edges, so all the kind of stuff that you also see in other deep nets when trained, but also in V1 of, for example, human brain. The second layer had the same learning mechanism, also unsupervised, but what we did is we introduced delays on the connections. And when you do that, it was actually learning spatiotemporal filters, and so it was learning local optical flow. And then we had a final layer, and there the same learning rule, but dense connections, and then it was learning global flow fields. And to us this was very interesting because in insects, they know that in the lobula plate there are neurons that react to different flow fields, like a diverging flow field or contracting or left and right. And so, yeah, we saw basically that if you have the same local learning rule without any supervision, basically, it was able to learn up till global flow fields. And so, yeah.
Interesting, thank you. Maybe I will ask later about this specific work.
Sure, sure, yeah, yeah.
Thank you for the nice presentation, by the way. I was wondering if you could elaborate more on where these drones, these tiny flight drones, might be used. Like, I think you mentioned SLAM, but I was wondering if you had any other ideas where you would apply them.
Yeah, very good question. Didn't touch upon that. Kind of assuming that we all think they're useful, right? So, but indeed, so the really tiny ones, one of the main advantages is that so they're small, so they're lightweight, so they're safe. And so bigger drones actually can be very dangerous for humans. And you see sometimes applications like I work a lot with greenhouses, so drones in greenhouses. And then they have a drone and it flies there. And people have to wear helmets and glasses and avoid a part of the greenhouse. So this is not the future I want. I want a future where the people are just working and you have these like, butterflies basically going around and you don't care. And if something goes wrong, because it will, so one of them will fall or whatever, there's no problem. So the safety is huge there. And also the fact that in indoor applications like greenhouses, but also in warehouses, like at IKEA, you want to know how many billies there still are on the top shelf. You can have these drones flying around, checking. And what is also important is that they're small and can move in narrow spaces, because indoors, already quite, it is actually pretty big space, but I mean, there are many spaces here where, you really need to maneuver and be small.
If I can still, then you have an idea, for example, the weight that they can carry, because you know, normally they use these big drones to carry some packages or something. But these tiny drones, how, like an estimate of the weight they can carry, for example?
Yeah, so the payload is limited, so that they can take on board for these applications. So the kind of thing we're thinking of, for example, in greenhouses, one of the important things is disease detection, pest detection. You can do this with a camera. Of course, that can be pretty lightweight. They're also interested in different spectra, like infrared or UV. In that case, we're thinking of a swarm with individuals, one individual with infrared, one with, but you have to be indeed, in terms of payload, you have to be very, I mean, you're limited. That's just clear. And so we're trying to find what are the best applications and the best sensors for those.
Thank you.
Yes, thank you for the very interesting talk. Maybe a small technical question on the last neuromorphic part. Can you put spiking neural networks into FPGAs, and or is that a part, like how does that compare energy-wise, and would that be possible to sort of put them on the 20-gram type of quadcopter if you directly read the camera with FPGA and then have the logic like sort of hard-coded as logic?
Yeah, very good question. So the short answer is yes. So yes, you can put it on an FPGA. You can program like spiking nets into there, and then it will be fast because it's like it can be executed in parallel. It will be relatively low power as well, so that's also positive. Of course, if you want to go even smaller, then yeah, you need to make a specific ASIC, like a printed circuit board, for that application. Then it becomes smaller. And so,
are you doing that?
So personally not, because I don't know anything about electronics. But I'm working together with many people that. So I'm working together with one group, like Charlotte Frankel in TU Delft, and she can make that electronics, but she also is doing the FPGA part. There's also companies like SynSense, and that's one thing we're working with now. So it's really a camera like this, with a chip like this, so tiny, and then like, yeah, what will it be, 2-3 grams? And on that, you can program a 9-layer convolutional spiking neural network. So we're now working on this, but it's challenging because their neural model is, it's an integrate and fire. Yeah, it's a bit detailed, but so it's very challenging to, for example, get this network that was on the Loihi on that one. And so you cannot use the same neural model. So it's challenging, but yes, you can get really to small hardware, and I think FPGA is part of the path to these really efficient, specific hardware.
Cool, thank you.
Yeah.
Other questions? Okay, then thank again, Guido de Kron.
Thank you.
Yep. Okay, so now we were organizing the schedule to leave a lot of time, free time available. And actually, we have another coffee break right now, so you can enjoy some more snacks and savory snacks this time, and some more coffee and tea. And we get back at well, 1 second. Let me double check. Put the slide at 3:45 for a short panel discussion with our speakers, so we can come up with some good questions to ask them and try to see robotics from the bigger picture and try to see what are the interesting trends and any questions you wish to ask but you were too shy to. Okay, see you again in almost 1 hour. Yeah, yeah, 3:45. Okay, so thank you everybody for coming back after the free food. We do still have some free drinks and snacks later, so there is still some incentive to remain for longer. But today we're going to have, right now we're going to have a very interesting panel discussion. So this is going to be just an informal talk about any questions you might have about the broader organization of the field and where we are headed. So we're going to ask a couple of questions to get started. Then we are going to give you the stage, and you can ask any questions you want within reasonable. Okay. Anyway, yes.
Test. Oh, there you go.
Can I make a comment? I've been to many talks, but I've never seen all the speakers being bombarded with questions after the talk. So well done with the organization. Well done to the people here today. But yes, we can answer more questions again. I mean, we have been really bombarded. I've seen people surrounded by 10 people at least.
I think that everybody is very grateful for our amazing speakers.
Well, and it means also that the audience is very curious and very, interested in the things that we are discussing today. So well done to the organizer as well.
We're also very happy with the variety of profiles in our speakers. So we really covered quite a big chunk of different subfields of robotics. So that also was quite interesting. And related to this, the first question I wanted to ask is, what do you think is the most pressing concern in the field of robotics? What do we need to make robots scale and really be widespread? Anybody who wants to answer?
Well, I'll start. It's a very pragmatic answer, and it's very deep mind as well. I mean, it's very different what I would have answered a few years ago. But what I've seen is that if we can have the data to clone human intelligence, like in the language models that in these days are a very clear example of how we can clone a particular type of intelligence, which is the one of producing text and reasoning at the text level, then we can solve or get a tool that is very different from what we had before. And in the context of robotics, it means being able to have the data to clone human motor control intelligence and possibly couple this intelligence with text and images, which we already know how to manage. So I would say it's a little bit boring answer, but a good data set of demonstrations of tasks coupled with images, video, and text could go a long way to understand how robotics can be solved. As I said, very deep mind, very data driven, but yeah, I really believe in it, unfortunately. Simulations can help as well, so not just demonstrations through, first person demonstrations.
My answer is also going to be very boring. Actually, it's the next step after what you were saying. So just a thought of how do we bridge the gap between having this intelligence with the AI and machine learning to having it certified, safe, and really practically applicable. So that's on the one hand the whole algorithmic development, but on the other hand also a big societal, political, policy development step.
So this is really not going to be boring. No, sorry. Perhaps it is, I don't know. So to build onto that, so they should do something useful, right? So I think if it really wants to scale up and companies are going to use it, and it needs to do something useful, quite reliably, so, part of it is in what you say. I think part of it is also in making failure acceptable. So that's, we talked a little bit about it after my presentation, like if your robot fails and then it's so lightweight and it doesn't hurt anybody, becomes acceptable, more acceptable. But I also think online learning. So there's like, so robots that can adapt on the spot. And I think this is a topic, so things like self-supervised learning are typically studied with data sets. But doing the learning on the robot while it's operating, it raises a whole new set of questions, but it will allow robots to keep functioning in different environments. And how to set that up so that it works, that's, I think, one thing we're missing.
Okay. I like to be the devil advocate here. Yes. Tactile everywhere. No. I also like the distribution of seats, because I think that Francesco is the person I disagree most, and as it gets closer, I agree more and more. We can hug. So from my perspective, I think that the two things that we need the most are, first of all, robots that do useful things. I agree with Guido. I don't personally believe that we need a general artificial intelligence that solve everything before we can have robots that are actually deployed at scale. I think that if they only do one thing, but they do it well enough, that people are say, okay, I can buy this. This is actually useful. I would have it in my house. I would have it in my factory. That's a really big enabler. The second aspect where we think we have made huge progress over the last 2 years is price point. It does not matter how good a robot is. If a humanoid robot costs you 1.5 million, you are not going to buy it. A factory is not going to buy it. In the moment when a humanoid robot does one thing well and it costs you 10,000 euro or 100,000 euros, that's the moment when you will be able to really put these things at scale into the house of people or into factory, into our society. And once you do that, then over time, over decades, you can give them more and more capability of being more general, being able to adapt to more things, being able to solve more tasks. So in some way, I think that what we are seeing now with the decrease in price is spectacular. It's exactly going in this direction. And on the other side, the hyper-specialization, for example, of the iRobot that sell cleaning machines, these robots that go around and clean your carpet, this is a good thing. They have a clear market. They can produce something that is cheap enough that people can buy. This is my opinion. So.
If this is going to be a debate, I can, immediately answer. Otherwise, if we're gonna, I have a few answers.
We're happy to really hear different opinions and back and forth. We are very happy with that.
Yeah, no, I have a few things. I think that's very, maybe it's a little bit of a game. Now, in these days, it's very popular at conferences to just do the debate for the sake of the debate. So I can try to defend my cause, and then Roberto can do the same. And then at the end, maybe we reveal that we are actually thinking the opposite of what we were trying to advocate for. It's kind of a fun game.
You make up over drinks.
Yeah, exactly. And then we can hug at the end, so we get closer. It's touching on many things, but I don't know where to start from. So one thing I want to follow up on Guido in particular. He mentioned that already, but I want to stress on it in particular. I think the bit on robots that fail and they are more acceptable, it's a very good starting point. I really like it. And it follows up on what you were trying to say. If you talk to industries, and as you can imagine, I've been talking with industries a lot, and they basically mention this, 99.9% accuracy with 9 decimals of nines, and if it feels like it's totally fine for the existing business model, and it's totally fine for the kind of automation we have nowadays. You were mentioning one thing that can be done in an efficient way or in a very practical and minimal errors way. I think we already have that technology. We can build cars, we can build cell phones, and you go talk to Foxconn. Foxconn will price the cost of automating the assembly of anything you have around you. They will just say it's an upfront cost of a few billions. You need to produce a few billions of items, so it becomes £1, €1 on top of your cost of what you're trying to produce. But it's an upfront cost for the automation. I will do it perfectly, and it will allow you to save a lot of money. So it does one thing. It's just that particular model of the car. It's that particular model of the iPhone, and the cost is really, really dropping down. And that's why I think generality is appealing. And that's why maybe 99.999% is not great. Like, you can accept some failure if you open up a new thing. And I know that, for example, from SMEs, small and medium enterprises, that's a more effective kind of use case, right? Because they don't have millions of copies of their goods. Like, they produce 100 if it works well. and they don't need certain level of precision. They can be a little bit more flexible on certain things, but they want to customize things for the users, for the customer at the end. And I think this is opening a good use of new technologies, new ways of doing things, and perhaps a new way of looking at what it means to have a machine doing something else for us. More, basically like two axes: accuracy, repeatability on one side, and generality and flexibility on the other one. And I think it's an interesting, exploration as a research scientist. I might agree that we're just fine going ahead with this business model and the things we are doing now, but I think it's very thought-provoking as well to think in these dimensions.
I would partially agree, but I think there's also quite a lot of industries where you have these kind of very repetitive tasks, very narrow domains that you can't automate yet. So in particular, think about agriculture and food production. There's huge problems in labor shortage in the Netherlands, also in the UK with the strawberries in Wimbledon. So I'm a bit more on their side that at least for some applications and domains, it's probably still worthwhile to have a more narrow system.
Maybe an interesting factor here is, I think that maybe with Francesco we have slightly different also applications in mind, because you're talking about factory that potentially produce billions of parts, where in many cases I'm more thinking about a household environment or a service environment with humans. Now, if you imagine that you have a success rate of, let's say, 95% when grasping, an object, and you're a robot barist. Well, you don't want to break, 20 glasses a day by failing 5%. So there are cases where, especially with interaction with humans, you do actually want to have 99.9999999, or to have a very safe way of failing, because otherwise that influence directly humans in a way that is probably, well, not nice for humans. Well, if you fail in a factory, you say, oh, I produce a car that doesn't work. Well, I can just throw it away and move on to the next one. That's okay.
Okay, one thing to add. So, yeah, in your video, you had these robots failing in ways you wouldn't expect, right? And I think that's still the case even with computer vision. Although we get great performance, it still fails in ways that we wouldn't fail. Yeah, so there's this group, I don't know where, but they made this sweater, and then the deep net doesn't recognize the face anymore. It's a pretty cool sweater, pretty colorful. But and I think so we still also miss some understanding of these deep nets, and there's probably still improvements that we need if we want to really nail perception, for example, like and where do the failure cases come from, right? And I think there's part, although perception is pretty good, there's part in perception, and there's a big part in interaction. So because the drone market is one of the biggest ones, but why? Because these drones, they fly high in the sky, they use GPS typically, and they don't interact with anything. And so in that sense, I really agree with you, touch, but yeah, interaction with the environment in general, that's actually very challenging. Yeah. I don't know if this made sense.
Maybe we can take another question. I have answers, but I think it will be an endless discussion on a topic. Maybe it's not of interest for everyone. I'll address Jens later on a one-to-one basis,
yeah, so
on a fight.
It's actually a very interesting discussion, but I was just thinking about the last thing that Guido said, and also with Roberto, about the interaction and the challenge with interaction between the robot and environment. And I was curious to see your opinion about the necessity or the role of embodiment, in achieving high degrees of general intelligence in a robot. Is it necessary, or do we really need it, or is it unavoidable, for example? And that, I think, will connect with the interaction.
According to my definition, if we don't have an embodiment, we don't have a robot, so your question is mute.
Very German answer.
So, okay, compare it to large language models like GPT, for example, or Gemini. Okay. Can GPT or Gemini be artificial general intelligence without a body. Let's see this way.
Don't get him fired.
Yeah, that's what okay, we can skip Francesco and go to the other speakers.
No, I mean, so I must say I always, I was brought up to believe when I was a student, like embodiment is key to intelligence, right? So I must say that before I saw large language models like ChatGPT, I was thinking they would never reach that level of intelligence without embodiment. And now, of course, and then you see that, yeah, I mean, it doesn't do everything perfectly, and we basically don't understand what it understands exactly, but just by, you know, this self-supervised learning and also with text and now images and videos, and it's not exactly what we do, but we also, you know, learn how to correlate these things. So, and we also don't understand our own intelligence perfectly. And so I do think that it captures, yeah, a very essential part of what we are also doing as babies, like the babbling first, but later, you know, other sensors. And we also start to explore much more in a directed way our environment than by babbling. But so I do think that in a weird way it is kind of like our intelligence, and but in what way exactly? Yeah, I don't know. I wouldn't be able to say, of course. Yeah.
A very interesting take. Roberto, you also want to say something?
So I think it's a bit less clear cut if you think, so what do you define as without embodiment? So if you have a large model that effectively learned to have some kind of an internal simulation of the physics and its own body and the world, is it then embodied or not? So once these kind of models really have the capability of effectively simulating the world in some sense or other in a sufficiently realistic way, they can probably get quite far without having a physical body, but then what's the difference?
Yeah, I agree with that. I really agree. Honestly, my interest, scientific interest, has always been physical intelligence. So for me, I'm not very happy with the kind of intelligence that ChatGPT displays. And I agree with Jens, 100%. I think that that level of physical intelligence doesn't require a physical body, but a good representation of an environment that is complex enough where things can be moved, can be transported, you can influence the state of the environment through a sequence of actions which is very complicated, possibly through physical interaction, and that's like what the intelligence that I think it's really missing at the moment. We have a lot of the planning intelligence, we have a lot of other types of intelligence like semantic understanding, even logic to some extent. Image production is, you know, tools that we have nowadays. They're very, very smart or like represent a good representation of reality, but we're lacking what I really care about, which is the motor control intelligence, which animals do have. And, you know, it's, again, we're so far from it. Actually, I was fascinated to see Guido's videos because I think they're just, you know, I didn't think that was possible in these days, but, you know, imitating a butterfly to me or a fruit fly is something that is extremely, extremely intelligent, and you know, it resembles a lot of the ingredients of what I think is needed, if only could be more general than what we're seeing today.
Yeah, I think I subscribe to all of this. I think that the problem is the Moravec paradox. The hard part of intelligence is not planning, is not talking. I think it's the hard part of intelligence is opening a door or learn how to grasp an object. This is what's hard. And all the examples that we have in nature of intelligent systems, whatever intelligence is, are embodied. You know, there are people, it's animals, it's systems that have a body. We don't have any concept of intelligence without a body. Now, there is a more fine discussion that I will not go there, but I'll tell my opinion. About whether, you know, these large language models are intelligent. And there are many different aspects of intelligence, but in Silicon Valley, a lot of people are convinced that systems like ChatGPT are intelligent. I disagree with this because they are basically just, yeah, they're just designed to mimic humans. They're not designed to really think. And to plan and to know how to solve things that have not seen before. But this is my opinion.
Does anyone have a question you want to ask? Okay, Heike.
I'd like to follow up on the question of embodiment or this discussion on it. So robotics often consists of components, and those components are quite standard, and they have been built with conventional control in mind. So servo motors, drives, sensors. Do you think that now that we use very different control structures, we should also look for different types of components? Do you see new types of components emerging and becoming standard?
Yeah, I love this question. I think it's beautiful. I think that there are two aspects of this. The first one is that I think that a lot of the times when we build a robot, we already have a very specific task in mind of how we want to use it. But at the same time, we try to make them somewhat general enough that they can be, sold to many different customers. One of the line of research that we do that I've not had the time to discuss today is about basically learning together hardware design and control design, with the idea that if you have a robot that is only designed to do one task, you probably want to hyper specialize it to solve just that particular task. And this is in some way also a learning process, can be framed as a learning process, in the same way that evolution sort of has evolved our body over hundreds of millions of years to be able to fulfill a specific task, which is to survive in this particular environment where we are. The other aspects of this, which I think is very interesting, is whether we should have robots that have sort of human shapes or human concept in terms of sensing, in terms of, I love to work with multi-finger hand because they're as dexterous almost as human hands, but from a natural point of view, this is super inefficient. Why not have tentacles instead of fingers? That might be a lot more dexterous, might allow us to do a lot of more things, but it doesn't look quite as good, and maybe it's harder to build, and it's harder to then control, at least analytically. Yeah.
Yeah, I think it's a very nice question because we're also limited by the technology in a certain way. And this means that the intelligence, the artificial intelligence that we make for robots is going to have basically different properties. And then the question becomes, what should we try to develop as well? And one of the things, I typically see is that, you have sensors that are, and computers that are quite general and modular. Then you place them together, your system is actually bigger than it has to be if you would, design something specifically or evolve body and sensors for a specific task. And and one thing that I was just a balloon thought, we typically centralize things now. So there was the video of the not so nice experiment with the cat, right, where they sever, the head from the spine, where it's still walking. But it shows that a lot of our, there's more than just the brain, right? But most people think in terms of, camera with like a central processor and then, wires that go to some servos. But if you look at our bodies also with touch, it's like distributed, like hairs. It's like, but they're also part of the control is actually elsewhere. So, and this kind of thing, in robotics is not yet common because practically it's much harder to investigate than to buy modules and put them together centrally.
I was going to say something very similar. So many of the components, standard components we see, are indeed designed for this kind of very centralized control approach. But then with machine learning and artificial intelligence, that has also opened up the avenue to control systems that are traditionally very hard to control. So think of under-actuated systems, soft robots that then indeed push part of the intelligence more closer to the hardware or the embodiment.
Couple of considerations. I agree with most of the things that have been said before. But good question. I think I really like the question. That's why everyone has something to say. Following on Guido's talk, I think there was an interesting bit of what you're asking. So the use of event-based cameras, right? I remember when I started working at IIT, we had like people working on event-based cameras and figuring out how to do the signal processing and somehow connect it to the execution of a task was kind of a difficult problem, especially if you want to put model-based on top of it, because a camera, like an image, a static image, is very easy to understand. If I look at the flow of images of an event-based camera, I don't get a sense of anything. So I think it's already changing, if you want, or in this case, the technology was already around, and now we can make use of it in a different way because of the technology. The other comment that I had is to please Roberto instead. I mean, tactile is another one. I worked with tactile for quite some time, and tactile is a sensor that is supposed to give you a pressure, a force distribution between two surfaces that come in contact all of a sudden. So it's a distributed force and pressure sensor that gives you the geometry of the interaction, and it's very rich. But if I look at a tactile image, I don't know how to make sense of it. And still I know that for physical interaction, tactile is fundamental because it gives you exactly this force distribution and a sense of the surface and a sense of how much force I can apply. Is it slippery? Is it not slippery? There's many information conveyed, but it's so non-model based that for ages I was like trying to put a model hat on top of it, and it's not much I can actually pull out of the sensor itself. But I know the information is there. I know that certain type of sensors can measure that information. I know how to process it. I don't know the features, like the classical audio features or corner detection that you have in images. They don't apply to event-based cameras. They don't apply to tactile, which is itself a sort of event-based sensor. And finally, I think that honestly, these data-driven approaches with intermediate representation that we don't really know how they work, but they do the end-to-end task. Opening a way to use these technologies that was not possible. And then final remark, I honestly think that we are just talking about sensors, but there's another part on the actuation side, which you were also sort of anticipating or hinting to. We do have this idea of motors like voltage in, movement out. Muscles are completely different. They are like complicated parallel actuation units that can be activated simultaneously. Similarly to other sensors that I mentioned before, there's in Japan many groups, like invite you to check what they're doing, because they're really building humanoids with fiber muscles, like by the tens for every joint, so 10 times 50, you have like 500 muscles in the entire structure. And they can do some model-based approaches, like, of course, I can flex the hip and I can balance, but it's very rude and rudimentary and simple tasks they can solve. Again, I honestly think that this more end-to-end approach where you just inject some sort of actuation and see how this reflects, and building a representation of that, which is very end-to-end and less model-based, can really help in using these very complex systems that are eventually very complex to model and where intermediate representations are difficult to get.
Yeah, very good. So we have another question here, right?
So if I may just continue to follow up on this issue of embodiment. I was actually struck by folks on the stage saying that since like ChatGPT is not embodied, right? It's actually, I mean, having worked in computer science and robotics somewhat, I have yet to encounter any system that's not embodied, right? Because why? For example, ChatGPT, the graphical user interface is arguably its body, right? We tickle it with keystrokes, mouse clicks, then it actually, issues like fantastic text rendered beautifully on the screen, right? And so, if you say the large language models powering it is not embodied, that seems to be a category mistake. It's like saying a line of your code running your robot is not embodied. We don't just categorize in that way, right? So therefore, what is embodiment? Does it require like actual physical motion? Is it required for the system to deal with force? Yeah, what's really going on? Yeah, please help.
take the question. I mean, I go back to what I said before. You're right. First of all, I wanted to point out there's many different type of intelligence. So I think that's the emotional intelligence that we didn't touch upon, but it's a very important one socially. There is mathematical intelligence. There is, relational intelligence. There is intuition, as we call it. And there's like ability to display intelligence in logic. Any of these are different. Some of them can be expressed more easily via text, some others are not. And I'm okay with all of these. It's just that it's not my interest in research. That's what I said before. And for when it comes to embodiment, immediately I'm like apparently all the other speakers, I was born and raised by saying, intelligence requires embodiment. So I'm kind of associating the two, but I shouldn't, because as I just said, there's many types of intelligence. So for me, my intelligence I'm interested in is the motor control intelligence, which again, as you were already saying, entails a complex environment, which is composed of things that do not move by themselves. They're like, I can influence the state of the things in the environment, but they require a certain level of action and resulting motion in order to get this physical intelligence through physical interaction. And that's what I really care about, because that's, as we were saying, this idea of having an environment which has its own state, with objects that can be moved through physical interaction. That's the kind of physical intelligence that often people associate with embodiment, and that's the one that I care about. So it definitely is like aligned with what you were saying. Yes, it has to do with motion, it has to do with physical interaction, it has to do with, if you want, the classical way of interpreting it, like planning and execution, feedback, adaptation, and many other things that are relevant for physical interaction. But again, we're talking about one type of intelligence that I like, and perhaps some other of the speakers like because of their background. But there are many others, and I see why Silicon Valley people might just say, ChatGPT is intelligent, because if you pose them logic questions, it can solve it. The embodiment is different. It is suitable for that kind of intelligence, because, as you were saying, fonts, text, and screen display is more than enough to display that particular type of intelligence.
I think it's a bit similar to the age-old question of what is a robot. Is a smartphone a robot? It can physically interact with the world by vibrating and changing the light, and I don't know what. Same for a washing machine. Some people would consider them robots. Many people won't. I think it's the same for embodiment.
I will answer in a intentionally provocative way. If I throw a ball and ask a dog to pick it up, the dog can. Can ChatGPT pick and bring back my ball? No, then it's not embodied. It cannot physically interact with the world. It cannot physically change the state of the world. I think that from a philosophical point of view, the closer analogy I can think of is a little bit the Socratic idea of the prisoner in the cave, where the prisoner can see the shadows of the world outside, can reflected on the wall. And I think that what ChatGPT and all these type of large language models do is that they capture one particular aspect of the reality in a way which is very much it's just a shadow of the complexity of the real world. It's not as rich. And through this shadow, they understand some aspect of the real world, and they can indirectly influence in it by talking back to us. But they cannot just reach out and go and change the real world by themselves. So I think that this is the big embodiment difference.
So
3 more questions.
I think I'll take the next one. Yeah. So we've seen so far very different types of sensors, actuators, even different ways of processing information. So we kind of know, allegedly, that the best models, even large language models right now, are probably a combination of other models to process images, and then like you had sound on top of that. And I was wondering, like, the difference with the human beings is that you kind of sense and you also perform actions with the same set of the same hardware, and you process information in the same place. So we have this kind of shift from robotics, in which at this point is mostly modular, to humans, in which is more centralized as in terms of software, and at the same time you have like sensors and actuators all in the same place. So what do you think might be the difference if AGI had to be achieved in robotics between something which is built quite different from a human and intelligence as we know it, as we kind of embody it right now?
Can you actually tell me what AGI is? Because
so yeah, it's I'm not talking about universal intelligence, but I think yeah, for example, like picking up a ball, understanding what a ball is, understanding what the action is, being able to like solve a general enough span of problems. Not only flying, not only picking or orienting an object, but like doing that and maybe even I don't know, explaining what you're doing, and also picking up a different object, and at the same time walking in a different room and doing a different task. I think that's quite general.
yeah, because to me, I really don't like the word general in AGI, because actually your story, so if you have a certain fixed set of sensors and a fixed architecture and actuations, then you can learn, you know, with your own embodiment about the world. An important aspect of which, by the way, is that what you do influences what you perceive, which is a big difference with yeah, many of the large language models or other learning methods. Like you influence what you see, and there's a high dependence between the samples you receive over time. But it's going to be very specific to your body and sensors. So yeah, so that's why the general part of AGI, yeah, I don't think it exists actually, or can be. Yeah, I don't like the. Yeah, I don't know if anybody has a better. I mean, I understand what you mean with AGI now, but yeah, I would like a definition without the general, or somebody. Yeah, perhaps somebody has a very good definition of why general, because I don't see that.
Well, I can try to follow up. I think there are two different aspects of this. The one you were sort of hinting to is the difference between the body that you know the biological intelligence has to deal with, and the body that eventually an artificial intelligent being will have to deal with. Right? We were mentioning a few differences there that are quite significant in general. So my understanding is that there is a level of abstraction for which eventually, if you have the ability to influence the environment around you, and you know the same environment I live in, and I see something else, being able to influence the state of that environment with the same level of intuition and flexibility that I can do myself, then I think I'll recognize that as a physical intelligence human, as a physically intelligent being, right? And I don't really mind if, you know, internally, and this goes back probably to the Ex Machina movie, I don't really mind what's inside, as long as they display that ability to influence the environment around them. In the AI, in the Ex Machina movie, for example, to the point of influencing you for their freedom. Like, that's very philosophical, of course. It's like a Turing test for consciousness, if you want. But to that level, I think that displays a lot of physical intelligence, because it's basically using you as a tool, which is like a tool that moves and does in its own will, for their freedom. That's like, it's another level of understanding it. It's a very, very advanced. And what I wanted to say is, and there's another level, which is a general intelligence, in a general that can control anybody, any kind of like, I can use this intelligence and can control Guido's body, my body, or a car, and then something else. And I agree that this one is a little bit flaky as a definition, because eventually we know intelligence once it's sort of connected to one body interacting in that particular environment. So transferring a specific intelligence to multiple bodies, or going from robots to humans to something else, I don't even know if they exist. It's like probably a little bit more a flaky kind of question. Go ahead, Guido.
Add one thing, Jens,
yeah.
Sorry, Jens, I'll give it to you in a second. But because, for example, CNNs, right? So convolutional neural networks. Yeah, they're inspired by the brain, but they work because they have an inductive bias that things that are close together, you know, they get processed together. And so, but then if you would make a robot system that has all the pixels scrambled, then actually you're destroying the very inductive bias that makes the convolutional neural network work. And then, because then one pixel is going to be multiplied with the kernel with a pixel on the other side of the screen, the whole concept fails. So I think general, yeah, it's kind of like a pipe dream, I think. And but yeah, so sorry, Jens.
I wanted to come back to your comment about modularity. I'm not a neuroscientist, but as far as I know, there's quite a few different distinct areas in the brain. They are obviously a lot more interconnected. You have things you got from evolution in terms of reflexes. Parts of your brain are evolved millions of years ago, and we learned how to override them. So I wouldn't fully go along with your argument that human and animal learning is learning everything jointly and in one go without having any prior knowledge and modularization in there.
Much. It was a fantastic discussion. For any more question, we can talk during the drinks. I just want to share first another round of applause for our speakers. And then we have a little gift package by Tilburg University. These are custom-made beers by Tilburg University. They have fun descriptions on the label, so you can just enjoy them. And here, sorry, it's okay, then another round of applause, and we are ready for fantastic. Now we're on to the last part of today's workshop. We have a specially invited talk by Sergey Levin, and I'm pretty sure that it's a researcher that needs no introduction. We are very happy for his presence in this workshop, and we are eagerly anticipating his talk that I'm sure is going to be particularly interesting. So please thank Sergey Levin, and we can get started.
For this talk, if you have questions, you should come to this desk and ask your questions, okay? We don't want to see the same accident that we have in the morning. So now, Sergey, stage is yours, and we can start.
Great, thank you. All right, so is this all fully audible? Okay, great. All right, so today I'm going to talk about robotic learning with large data sets, general purpose models for all robots. To start us off, let's discuss a little bit of perspective about how AI used to work and how it works today. So it used to be that if we wanted to solve a particular AI problem, like for example, image segmentation or image classification, we would collect a separate labeled data set for each task, typically a pretty large data set, get human labels for it, and then train a separate model. And we would do this for all sorts of applications, for classification, image captioning, NLP, sentiment analysis, summarization. Each of these would be a separate model and a separate data set. And these days, the way that we tend to think about AI systems is that we have a very large and relatively lower quality data set, maybe just data mined from the web, that is used to pre-train a very large unsupervised or self-supervised model sometimes called a foundation model. And then these models are then fine-tuned to downstream tasks or even just prompted in few shot to solve a downstream task. And this is the case for language models. It's the case for contrastive vision language models, for all sorts of other contrastive learning methods in computer vision and so forth. So let's try to map this idea onto robotics. Robotic learning today generally is kind of in that same place as AI systems used to be, where if you have a particular task you want the robot to do, like flipping a pancake or something else, you would train a separate model for each application domain with data collected for that robot, whether it's imitation learning or reinforcement learning, and it would really be specific to that setting, that robot, that task, and so on. So perhaps in the future, if we want to tackle robotic learning challenges, we'll have a large data set of all sorts of different robotic behaviors, which we'll use to train a giant unsupervised or self-supervised pre-trained robot model, the kind of robot foundation model, which would then be fine-tuned to particular downstream robotic tasks. And I think if we get there, this will put us in a much better place with robotic learning, because we'll be able to leverage the benefits of huge data sets and huge models without requiring huge data sets to be collected for every single robotic application. And this will actually make it much more practical to bring the full power of machine learning to bear on the robotics challenges. Okay, so how can we get these kind of generalist robotic foundation models? And if we want to try to think about that, maybe we can start again with mapping this back to standard AI techniques and ask, how did we get generalist models in other areas? Well, we can think of it as a progression where you can start with small, very task-specific data sets, then through a lot of brute force labeling, progress to larger domain-specific data sets, maybe like, ImageNet versus MNIST, and then eventually get to very large and kind of domain-agnostic data sets of the sort that are most widely used in NLP, like Common Crawl and so on. And you can think of these different data types as being on a spectrum where the further you go to the right, the bigger the data sets become, but also the models become more general. The reason they become more general is because there's only a limited amount of data for each application. So if you want a huge amount of data, it'll have to be across applications, which means that the models will have to be more general. And that's both a good thing and a bad thing. It's a bad thing because it's, of course, harder to build a general model. But perhaps the other subtle but very important point is that the data becomes worse. The labels become weaker. If you want huge amounts of data, you probably can't rely on that data being extremely specific to your desired target domain, nor can you rely on that data having extremely good labels. And that means that your learning methods have to make fewer assumptions. So to get generalist models, the biggest enabling factor is the ability to use more data. And therefore, if you want to map this onto robotics, the question is how you design robotic learning methods that can use more and more data without necessarily making those strong assumptions and being able to leverage weaker data sources. So what kinds of data can we use for robotic learning? Well, we have high quality data, which would typically be single task and single robot, and also strongly labeled either with optimal actions for imitation learning or optimal task rewards for reinforcement learning. Then you can progress further to the right and have multitask data, perhaps less optimal demonstration data, or even fully suboptimal autonomous trials. Further to the right, you can have multi-robot data that is not specific to either the task nor the robot type. And then even further to the right, you could even include video data, which is not even specific to robots, but still depicts activities and behaviors that you might want robots to perform. So as our learning methods improve, the more they can move to the right on the spectrum, the more data they'll be able to consume, and the closer we'll get to being able to build robotic foundation models. So what I'll talk about in today's talk is some of the things developed in my group over the last year or two that I think move us further to the right on the spectrum. I would emphasize that there is a lot of work yet to be done, but hopefully this will give you a sense for what kinds of ideas could move us further to the right and therefore closer to the robotic foundation model. So I'm going to talk about first goal condition policies, which relax some of the requirements for strong demonstration data. I'll talk about offline RL with rapid fine-tuning. Then I'll talk about learning from videos and action-free data. And lastly, I'll discuss some work on cross-embodiment robotic foundation models that can use data from many different robotic sources. So let's start with a discussion of goal condition policies. If we want to start working on large-scale robotic learning and robotic foundation models, of course, we need to start with some kind of data set. And one of the things that we've been doing in my lab at UC Berkeley over the last couple of years is taking this idea very seriously. So we collected a very large data set called Bridge Data v2, which is intended to support this type of research. Bridge Data v2 has over 60,000 trajectories and interactions with hundreds of objects. All the trajectories do have full language annotations, and there are 24 different environments. And that's really important because if you want to train policies on this data set that will generalize across environments and run in other people's labs in order for the data set to actually be like reusable by different researchers, then you need many environments to be present in the training set. And we've in fact confirmed that policies trained on the bridge data can be evaluated and used successfully by other labs other than our own, which is really, really important to really support this kind of research. The robot used in this data set is a low-cost Widow X arm, which is relatively inexpensive to obtain, and that's also important for making this kind of research accessible. But what I want to tell you about today is how data sets like this can be used to produce fairly general policies with comparatively few assumptions. So here's a very simple idea for how to train a generalist policy if you have a data set like this. We're going to do goal-conditioned learning, where our policy takes in the current observation, shown here at the top, and a goal observation, an image of what the user wants the world to look like. And you can produce this goal observation just by moving objects on the table yourself, taking a picture, and then essentially asking the robot to figure out how to reach that state. So the current image goes in, the goal image goes in, and the robot action come out. Very simple. Now, it turns out that there's a very simple training procedure that can allow you to train these kinds of policies. It's not a novel procedure, it's been known for quite some time, but it turns out that if you take this procedure and you use a good enough data set, really good things can happen. So the procedure works like this. You take your data set and you pull out a trajectory. And along that trajectory, you sample two time steps, an earlier one and a later one, in green and orange. And then you construct a training tuple where the inputs are the green and orange image, and the output is the action taken at the green image. So that's your training tuple. The reason this works is because you know that whatever action was taken at the earlier time step, the one shown in green, eventually led to the later time step shown in orange. That doesn't mean it's the optimal action to reach it, but it means that it is an action that in principle could eventually reach that orange state. Now, if you want to make this precise, there's all sorts of technical assumptions that go into this, but broadly speaking, this actually works. It's a very, very simple procedure because the subroutine for training after this is regular supervised learning. But crucially, it does not make the assumption that the data is either optimal nor annotated with language annotations or anything like that. Interestingly, the bridge dataset does have language annotations, but this procedure does not require that assumption, which means that in principle, it can use broader and more diverse sources of data. And here are some videos of this goal-conditioned behavior cloning policy trained on Bridge v2. Now, again, the training procedure here is not a novel contribution of this work. It's been known for years. What is new is the particular data set. And you can see that the policy trained on this data set with goal-conditioned BC can actually perform a pretty broad range of tasks. This is the same exact policy performing all of these tasks. And you can see that it can sweep up dirt, it can fold cloth, it can open drawers, all with one single neural network, just by basically having the right data set. Now, of course, goal-conditioned policies are probably not the thing that we actually want in the end for robotics. We'd like humans to be able to communicate with robots in intuitive ways, for example, by using natural language. So what we would really like to do is retain the generality of this approach, the ability to use all sorts of unlabeled trajectories, but somehow retrofit the ability to follow language instructions. And we've explored a number of ways of doing this. One way of doing it is to use large amounts of data without language annotations, and then a small amount of data that does have language annotations, and somehow combine those two sources. So this was done in a paper led by Vivek Myers called Goal Representations for Instruction Following, where the idea was to build an aligned space that contains both goals and language instructions, so that you could have a small amount of data with language instructions and a large amount of data without it that is used for goal-conditioned behavior cloning. So essentially, the goal representation supports both images and text. This is conceptually very similar to CLIP, for those of you that are familiar with it. The main difference being that now, instead of embedding images and text into the same space, it embeds pairs of current state and goal state, basically a change in state, into the same space as a textual instruction. There's quite a bit of additional machinery needed to make this actually work in order to have the policy support this cross-modality goal representation. But broadly speaking, the procedure ends up being very similar to goal-conditioned BC, just with a representation that aligns text and images. And if you can do this, then you can train on the same bridge data set using only a small fraction of the textual annotations, and then carry out a wide range of language commands, significantly more effectively than alternative methods. So these results, the orange bar shows a success rate of this method called GRIF. The blue bar shows what you can think of as a goal condition BC method without the alignment technique. And BCZ, the gray bar, is a more traditional behavior cloning approach that performs imitation learning on the language label data. And you can see that in 2 out of these 3 scenes, there's a very large improvement, more than 2x, from using this alignment technique. Again, this is one of the ways that we can use lower quality data because we do not require the assumption that all of the data has those language annotations, and we can use data that is unannotated and perhaps lower quality. It turns out, though, that we can actually incorporate language instructions potentially without having any annotations at all, or leveraging internet scale data with annotated images without necessarily requiring those annotations to be on the robot data. So the way to do this is to actually leverage recent advances in image generation models such as diffusion models. So what we can do when given a command, like put the orange crayon in the wooden bowl, is instead of training a policy that can interpret that command, we can train an image generation model that can look at the current image that the robot is seeing and the instruction, and then actually synthesize a new image that depicts what the scene would look like if the robot were to execute that instruction. So the synthesized image for put the orange crayon in the wooden bowl might show the gripper over the orange crayon. And now, if we can build this kind of generative model, then the robot only needs to know how to follow image goals. So we can use that really simple goal condition BC technique from before, and now it would actually be able to follow language instructions because the diffusion model would turn those language instructions into images. Now, one of the nice things about using an image diffusion model as the way to interpret these instructions is that it's now very, very easy to incorporate non-robotic data into the training process. Here you can see 2 sets of goal images. Each one is produced for the same command. So the top one is fold the cloth from bottom right to the top left corner. On the right, you can see the image generation result from a model that is fine-tuned on both the bridge dataset and the something video dataset. Now, that video dataset depicts humans rather than robots, but the image generation model still only operates on images, so it's very easy for it to use video data from the web to assist in this fine-tuning process. Here are some results. So this is the synthesized image for a goal, for a sub-goal for the instruction shown at the bottom. And then after each synthesized sub-goal, you can see the robot actually performing that sub-goal. So you can see that the model doesn't just generate the final image for the task actually being completed, it actually guides the model along with the individual sub-steps. So here's the final sub-goal, and the robot performs the task. So the diffusion model guides the robot along through each step of the task, and the diffusion model benefits from lower quality data, such as video data, that is sourced from the web. And again, this is important because this shows that we can use data from more sources. In this case, we can use data from the internet that is not robotic data to assist in training the sub-goal predictor, and then use the goal condition BC model trained on the bridge data to actually execute those sub-goals. Okay, so that's goal condition policies. But now let's talk about moving even further to the right on the spectrum and being able to use even lower quality robotic data. So one of the ways that we can use suboptimal data is to leverage offline RL instead of imitation learning. What do we expect offline RL methods to do? Well, some simple intuition, which is maybe a little bit misleading, but pretty common, is that offline RL is like imitation learning, that maybe in offline RL, you have trajectories that perform a task, and it allows you to imitate those trajectories better. But that intuition is maybe a little bit inaccurate. A more accurate picture is that offline RL is kind of about getting order out of chaos. So if you have a variety of trajectories that go in all sorts of different places, maybe many of them are completely suboptimal, if you just take the bits and pieces of the individual behaviors and recombine them in a new way, then you can perform a task much more optimally than any of the individual examples that you saw, essentially using the examples to figure out what is possible, and then from knowing what is possible, figure out what would be optimal for your task. And of course, there's a simple version of this that happens kind of at a macro scale, where if you've seen an example that goes from A to B, and you've seen an example that goes from B to C, you should be able to figure out that it's possible to get from A to C. But the real promise of offline RL is that this kind of happens everywhere all at once. So if you see lots of suboptimal trajectories, if you recombine the very best parts of them, you can do better. Imagine that you have data of driving from lots of human drivers. If all of the human drivers are suboptimal in different ways, if you combine a new policy that is as good as the best driver in each situation, you will overall be significantly better than all human drivers. Most current offline RL methods are based on Q function estimation. I won't talk in detail about how these methods work. What I want to really focus on are the robotic learning results that demonstrate how offline RL techniques can enable utilizing broader sources of data and therefore get us closer to robotic foundation models. But if you want to learn more about the methods, I would encourage you to check out these two papers, Conservative Q Learning for Offline Representation, for Offline Reinforcement Learning, and Offline Reinforcement Learning with Implicit Q Learning. These two papers describe some fairly widely used techniques. There are also much more recent methods, but these could serve as a decent starting point. Okay, so let me tell you about a robotic learning result that utilizes offline RL in a way that I think illustrates our ability to leverage broader data sources. So this was a result that was actually led by some researchers at Google, Yevgen Chebutar and Quan Wong, called Q Transformer. And the idea was the following. We had a system called RT1 that we developed at Google some time ago. And RT1 was an imitation learning system. It would imitate language instructions. And it could do some pretty exciting things. Like it, for example, could navigate to a drawer, open the drawer, take out some chips and bring them to the table. But it required high quality demonstration data. And at Google, we could collect this high quality demonstration data and it was okay, but the data was expensive and we needed a lot of manual effort to collect and curate that data. So we thought, well, what if we take these 38,000 demonstrations with language labels and add in unsuccessful attempts from the robot itself trying to perform these tasks? Now, in reality, when the robot attempts these tasks, sometimes it succeeds and sometimes it fails. But to make a really controlled experiment, we actually only kept the failed trials. So we just threw out all of the additional successful trials just to keep the comparison fair. So we really wanted to answer the question, does adding failed trials from the robot itself improve the policy over just imitation learning? And what we developed is an offline RL method that was suitable for training RT1 style models. RT1 is a transformer-based policy that uses tokenized actions. So we needed an offline RL method that could train transformer-based policies with tokenized actions. So this was essentially an offline RL trained RT1 model. Here's the idea. The model is a large transformer that reads in images and reads in textual instructions, and then it outputs per dimension tokenization of the actions. So for every dimension of the action space is discretized, turned into a token, and the model outputs that token. So to make this work with offline RL, which requires Q function estimation, what we actually did is we had each dimension of the action correspond to a different time step of an underlying discrete action MDP. So instead of treating robotic control as a continuous action MDP with every real world time step being an MDP time step, instead we had more time steps where every dimension is a time step, but now the actions could be discrete, which means the same tokenization could be used. So it's a discrete action algorithm with more time steps than the original problem multiplied by the dimensionality of the action. It actually does these Bellman backups across dimensions and then uses a method similar to contrastive RL, to conservative Q learning, to CQL. So here are some videos of Q Transformer performing a variety of language conditioned tasks. So the same policy was trained across many different tasks, dozens of tasks, in fact, and it can perform a wide variety of instructions. But the important results are the quantitative results. And here we're comparing Q Transformer QT, the first column, to a variety of different methods, Decision Transformer, IQL, and the rightmost method is RT1, the original imitation learning technique, which does not use those failed episodes. This is showing 3 categories of tasks. Within each category, there's a very large number of tasks. So the total number of tasks in our evaluation was on the order of about 70-ish. And you can see that there's more than a 2x improvement in the average success rate of Q Transformer over RT1, which means including those failed trials actually more than doubled the success rate, which I think is pretty remarkable because the number of failed trials is not that, it's actually smaller than the number of successful trials. And of course, they're all failures. So this really shows that once we switch to offline RL, we can really leverage much broader sources of data in the sense that we can use autonomously collected failed attempts. Now, what if we want to use offline RL to actually adapt to a new task rather than just doing better at the existing tasks? One of the things we could do is pre-training with offline RL. So in another paper called Pre-Training for Robots, led by Aviral Kumar and collaborators, we took an earlier version of the bridge dataset and we trained a model with offline RL, in this case, not conditional language, but conditional task ID, that could perform all the tasks in the bridge data set. And then we experimented with whether we could take a new task and then fine-tune with offline RL to that new task. Now, it takes a little bit of detail to make this work. The fine-tuning procedure actually recycles batches from the pre-training data set because the fine-tuning data is so small. Here, fine-tuning data was just 10 trials for the target task. But basically, the concept behind this project is to use offline RL for fine-tuning, very similar to how pre-training and fine-tuning is done with supervised techniques. And what we saw is that actually we could do this successfully. We could fine-tune to a new task that's structurally similar to tasks seen in the bridge data set, but different in some way. In this case, the task has a different environment and a different object. So the robot has seen tasks that involve putting objects into a pot, but other objects in other pots, and now it has to put a cucumber into a red pot in a new kitchen environment. We compared this technique, which we call PTR, to a variety of other pre-training and fine-tuning methods in the robotics literature. Perhaps the most interesting comparisons are the ones shown on the right. R3M and MAE are computer vision-inspired pre-training methods adapted to robotics that learn visual representations from the pre-training data and then adapt using those representations to the downstream task, in this case, the 10 trials for the target task. And you can see that PTR, our method shown on the far left, achieves a much higher success rate than these representation learning methods, which suggests that actually pre-training with offline RL to perform these tasks is much more effective than merely learning visual representations. And the other thing that we see with this approach is that as the network gets bigger, the performance of the downstream task improves. So the x-axis here is the size of the model, ranging from a small ConvNet, the Impala model, to ResNet 18, ResNet 34, and ResNet 50. And as the models get bigger and bigger, the performance of the downstream tasks improves, which means that we're actually benefiting from scale in the way that we would expect from large-scale machine learning techniques. Now, how about online RL fine-tuning? So far, the results I showed fine-tuned from 10 trials that are provided by a human, so it's offline RL fine-tuning after offline RL pre-training, but we can also do offline RL pre-training and do online RL fine-tuning, actually run regular autonomous trials and see if we can improve through iterative attempts. So here, the robot is fine-tuning to open a microwave door. Initially, it has a reasonable idea, but it's not successful. Then we run more online RL with a variant of CQL called CalQL, and the robot gets a little bit better. And then eventually it actually succeeds at the task and is able to open the microwave door. And here, all it's getting is supervision from a sparse binary reward, indicating whether the door has been opened. So the performance improves from 53% to 73% on all of the positions of the door. And if we just test the novel previously unseen positions, 13% to 60%. So offline RL can enable acquisition of new skills with 10 to 20 demos, and then using cheap autonomous data can actually make that even better. Okay, now let's move even further to the right on that spectrum. Let's talk about how we can use not only suboptimal data or autonomous data for downstream tasks. Let's talk about how we can better use data without any robots at all. And I already alluded to this a little bit when I discussed the diffusion project from before, but in fact, we can actually incorporate video data directly into the RL process itself with a novel technique based on a particular kind of Bellman backup. So before we get into the technical aspect of this, maybe a high-level question we should ask is, how should we think of video data in the context of robotics? Well, we have robotic data. Robotic data sets have to come from robots, and they might be a lot bigger than you think, like with things like bridge data and recent innovations like Droid, which is a new data set led by Chelsea Finn's lab. There are actually fairly large robotic data sets in existence right now, but they're still limited in size. So if we go to the internet and we get a huge data set of videos from the web, it'll probably always be better than the kind of robotic data sets that we can construct today. Video data can be mined from the web, recorded from humans, and so on. But then the question is, what does it teach us? Because clearly we can't get robotic actions from there because it doesn't even depict robots. So here's how we can think about video data. Let's say that you have a trajectory of a video, and you have two states along that trajectory, two images basically, a green one and an orange one. Well, one of the things you know is that orange comes after green. Like whatever happened in that video, the outcome seen in the orange image is possible to achieve starting from the green image, assuming that there's not too much stochasticity. Now, that's not very useful because what you want to learn is how to do control, not just what comes after what. But let's say that you have another video where one of the frames is similar, the blue frame is similar to the green frame, but then the video goes into a different place and reaches a different state shown in yellow. So now, because blue and green are similar, you should be able to infer that green can lead to either orange or yellow, because you have two states that are similar, blue and green, and they led to two different outcomes, which means that probably both outcomes are possible from the same state, provided that you have the right measure of similarity. And now this is a very useful piece of knowledge, because now you can actually use this piece of knowledge to learn about making decisions, because it suggests a certain branching structure that this nexus in green or blue leads to two possible outcomes, which means that if you prefer the yellow outcome and you find yourself in the green state, the yellow outcome is probably possible. So more precisely, if you're at green, you can reach yellow if you try to reach yellow, insofar as the world is under your control, which is an assumption that you make. So the key idea is to use videos to learn which outcomes can result from which states, what is possible from each situation. And this turns out to be a great way to initialize value functions, because value functions in reinforcement learning predict essentially what kinds of, how likely certain outcomes are to happen. And the particular kind of value function that we can train is something called an intention condition value function, or ICVF, which is a value function that is conditioned on state, an outcome, and an intention. An intention is a state that you're trying to reach. An outcome is a state that you actually reached. And this value function is a type of generalized value function, basically predicts the likelihood that you will achieve a particular outcome if you are attempting to reach that outcome or some other outcome. So it's basically directly quantifying this question. At green, I will reach yellow if I try to reach yellow, and it outputs essentially probabilities. These intention conditioned value functions, under some admittedly very strong assumptions, are provably sufficient for representing all possible tasks. So if you can train ICVFs exhaustively with infinite representational power and infinite data, they will learn all possible tasks. Of course, with a finite sample of videos, they won't learn all possible tasks, but they will still serve as very good initializations for downstream RL. So that leads us to the following procedure, which we call VPTR, or video pre-training for robots. First, in phase one, use this ICVF technique to train a generalized value function on human videos. And this generalized value function will serve as an initialization. It will serve as pre-training for phase two, where we will run the PTR procedure from before on a smaller amount of robotic data. And imagine that you might have 4 million videos and, 70,000 videos, 4 million frames for the natural videos, and then you might have 150,000 frames or 3,000 trials for the robot data. So more than an order of magnitude step down in the size of data. And then in phase three, you can fine tune this to the particular task you want, some fairly difficult task like sweeping up dirt, using just 10 trials and a few hundred steps. So each step serves as the pre-training for the previous one. So this is VPTR. I could, of course, go into a lot more detail, but I don't want to run out of time here. So if you want to find out more, check out this paper called Robotic Offline RL from Internet Videos via Value Function Pre-Training. In terms of the results, VPTR actually works pretty well. Now, these are fairly difficult tasks. Again, they still have lots of room for improvement. These tasks have more distractors in them than the tasks I showed before in the original PTR evaluation. But one of the interesting things I want to draw your attention to are the two rightmost columns. The second from the right shows regular PTR, which doesn't include the video data. The rightmost one actually omits phase two, so it has videos and the downstream task, but doesn't have the large-scale robot data. And you can see that omitting the video data is, in this case, like pretty much just as harmful as omitting the robot data, which means that both sources of data are actually having a big benefit. And that really illustrates that this is truly moving us further to the right on the spectrum, where we are fruitfully making use of both larger multitask robot data sets and non-robotic video data sets. And we can do this for language condition policies too, and that also leads to significant improvement over regular PTR. Okay, so now we've moved a little further to the right. In the last section, I want to talk about how we can get even closer to true robotic foundation models by leveraging data from many different kinds of robots. So the first thing I want to tell you about is some of our efforts on building a robotic foundation model for navigation. This work is actually a little bit older at this point. It's about a year and a half old. And it started with a project called GNM that was led by Dhruv Shah and Ajay Sridhar. The idea was to take data from a variety of different ground robots and try to train one model that could control all of these robots together and see if that leads to significant benefits. So what we did is we collected both our own data sets and also data sets that others had posted on the web. Turns out that these data sets came from 6 different types of robots, ranging in size from small-scale RC cars to full-scale ATVs. About 60 hours of data in total. And then we used that data to train a goal condition BC policy, very similar to the one that I presented before at the very beginning when I talked about bridge data. with the main difference that this goal condition BC policy now took a context window, essentially showing the history of recent observations from the robot. And that context window is important because it allows the model to determine what type of robot it's actually controlling. It turns out that this model could not only control the robots seen in the training data, it could also actually generalize in zero shot to entirely new robotic types. What you're seeing in the top left here, for example, is a video of a drone flying through hallways. There was no drone data in the training set. The training set consisted entirely of ground robots. Now, I will say this drone is pretending to be a vehicle because the drone is flying at a fixed altitude. So the control is still like a car, it's directional. But it is a different robot. It has a different camera. Obviously, its dynamics are different, but the model can actually generalize and successfully control the drone and avoid obstacles flying through hallways. Here is a kind of a montage of all sorts of different systems in all sorts of different environments that are all controlled by the same exact neural network. One of the things that this model can do is it can actually generalize effectively to changes to the robot. So we could, for example, introduce some damage where, in this case, a stick is placed into the wheel, which changes the robot dynamics. After that damage, a naive model will actually not steer the robot correctly, but the GNM model, because it's seen many different robot types, it can actually generalize to the damaged robot as though it was just a different type of robot and navigate it successfully to a destination. And here's again that video of the drone. So here you can see the current observation in the bottom left, the gold image in the bottom right, and it's successfully flying the drone through a hallway. We more recently extended GNM to use a large-scale transformer-based model to further improve its generalization capability and its ability to utilize large data sets. So we call this the visual navigation transformer. And this is now an open source model. You can download it at this URL. A number of people around the world have actually used the visual navigation transformer VINT for a variety of downstream applications. Here are a few different robot types that are controlled by VINT, legged robots, indoor robots navigating different destinations. You can do prompt tuning with VINT, so you can actually replace the goal encoder with a different type of encoder for some other kind of instruction, like, for example, turn-by-turn instructions out of Google Maps. And you can do things like adapt VINT to actually do driving in Carla. I apologize, the video is not playing, but this is in the Carla simulator, adapted from a small number of trajectories. I can follow turn instructions like turning left and turning right. We can also do RL fine-tuning from this kind of multi-robot pre-training. So in this project called Faster Lab, what we did is we performed, in this case, actually offline RL rather than goal condition BC pre-training, but very similar to the GNM project, from a multi-robot data set. And then we perform online RL fine-tuning from that initialization. And the online RL fine-tuning process actually ends up working quite a bit better. I apologize, let me restart this so the video plays. There we go. So the online RL fine-tuning works quite a bit better than it does from scratch. With online RL fine-tuning, after just 15 minutes directly from raw pixels, in this case, the robot is trying to race around this indoor track, it can actually more or less navigate, albeit slowly, and after 25 minutes, it can actually race around this indoor course going around the hallway at more or less the same speed as an expert human, in this case, the graduate student that was doing this project, if they use the same first-person camera. So here's the first-person result. This is just 25 minutes of online RL training. 25 minutes of online RL from raw pixels typically wouldn't yield a useful policy, but because of this offline RL pre-trained model that uses the multi-robot data, it can actually do this successfully. And the multi-robot data used for pre-training doesn't actually include any data from this robot. Here is a similar result outdoors. So this is the initial policy before the online RL phase, and you can see it's doing something, but it's not doing too well. But then after, again, this is about 30 minutes of online RL training, it can actually race around this course successfully and will exhibit some interesting behaviors where in between the checkpoints, so the checkpoints are on the grass, it'll actually prefer to drive a little bit on the paved paths so that it can go a little faster. So there it goes on the paved path and can go quicker on the paved path. And here's the first person view where you can see just how shaky the camera is. So this really is a fairly difficult task because of the amount of camera shaking and the complicated dynamics of driving on bumpy ground. One question that we were really interested in with VINT is the degree to which these multi-robot policies are actually deployable in other domains. And it turns out that it actually does work around the world. And every few months we get some emails from folks that have used VINT or later models like Nomad in their own settings. So this is a result from a university in Estonia that used a variant of the VINT model for an orienteering task where they had a ground robot driving outdoors through the Estonian countryside for hours and hours trying to find particular locations. Here is a result from Finland showing a ground robot navigating their university campus. And their research was on, as I understand, on topics related to semantic navigation. And they essentially used Vint as a plug-in low-level controller just to perform the low-level control task so that they could study their interesting high-level semantic navigation problem. Here is a result from Princeton. This was a comparison. So the authors were developing their own controller for these drones, and they compared it directly to our controller without any modification, just directly using our weights, without training it on their system. We can demonstrate these robots in real-world settings. So we took it to a conference and had the robot drive around, avoiding humans. Interestingly, the model was not actually trained in the presence of humans. It was trained in a lot of forests. So I think it probably thinks the humans are trees, similar kind of profile, and the obstacle avoidance works. Now that's for navigation. Of course, we could ask the same question about cross-embodiment training for robotic manipulation. And recently, we studied this question in the context of the RTX project. This was a very large project, a cross-institutional collaboration, but it was led primarily by Quan Vong and Carl Perch. The idea in RTX was to take a variety of data sets, including the bridge data from before, but also many other data sets from 34 different labs, and combine them into one giant cross-embodiment data set with 22 different kinds of robotic arms, 527 skills, and 60 different data sets in total. Now, all of the arms were end effector controlled 6 or 7 degree freedom arms with parallel jaw grippers. So the hardware is not that heterogeneous, but there is a lot of variability. And just to emphasize the variability, here are videos of the different kinds of situations depicted in this data. So you can see very different camera views, very different objects, very different tasks. The statistics for this are in the data set, and there's a really nice visualizer that my student Debo Ghosh built that you can access at this URL. It is a very heterogeneous data set for robotic manipulation, probably the most heterogeneous one in existence. It has about 1 million trajectories in total. Now, one of the things we were very curious about is whether a single policy trained on this entire data set could actually improve over individual specialized policies in each domain. Because something that we've seen in other areas like NLP, for instance, is that specialized solutions, like I mentioned at the very beginning of the talk, for things like text summarization or sentiment analysis, are outperformed by modern foundation models that are truly generalist models. So if we train a generalist model on the RTX dataset, does it outperform the individual specialists in each domain? And here are some of the tasks that we were testing. These tests were conducted, again, by a number of different universities around the world, from Freiburg to New York to UC Berkeley. And on average, across the different institutions that tested these policies, they found that the cross-embodiment policy was, on average, 50% better than whatever method that laboratory was using for their own tasks. And I would emphasize that each laboratory had a different method that they were using for their tasks. It was whatever was the best method that they had developed in their setting. And this cross-embodiment model, this one is called RT1X, actually outperformed it on average by 50% in terms of success rate. We also trained a large-scale vision language model that was fine-tuned on the RTX dataset and tested at Google in comparison to the best vision language model that was trained on Google-only data on fairly nuanced semantic tasks that required repositioning objects based on textual command spatial relationships. And we found that on our hardest generalization evaluation, the model trained on cross-embodiment data improved by over 3 times in terms of success rate over the model trained on only the Google data. And this is very interesting because the Google portion of the data set was actually the largest portion. It was over 130,000 trials out of 1 million. So even the robot that had the most data available to it improved by 3x on the hardest generalization tasks by leveraged data from other robots. And here are more examples of these kinds of semantic tasks that required this high degree of generalization. So this is pretty interesting to me because it suggests that including data across many different robots can actually make models in each domain better than specialized models trained in only that domain. And that's really, I think, bringing us very close to that dream of a robotic foundation model. So to summarize, I discussed some steps we could take towards a robotic foundation model where we can have data from many different robots that we could use to train a general purpose model with some kind of self-supervised objective like goal conditioned learning. For example, predicting actions at temporal distances, and then adapt it to a variety of different settings, fine-tune it with RL, or even utilize it for downstream instruction following. And I discussed a few different building blocks, a few different pieces that we can recombine in this way. But of course, in the future, we might want to put all of these together and get one truly general and broadly applicable robotic foundation model. I'd like to thank my students and collaborators, my collaborators at UC Berkeley, as well as my collaborators at Google Research. And I'd like to thank all of you for listening. And I can stop now and take questions. Thank you very much.
Okay, thank you very much, Sergey, for this engaging talk. So from the audience, if you have a question, please come closer to the PC in here and ask your questions here. Come on, we should have a question, I guess, no, after this talk. Yes. Please talk to the microphone.
Okay. Thanks a lot for the very interesting talk. So I have a question regarding this, combining these different pieces of demonstration. So essentially, do you need some kind of reasoner for doing it, or you can do it purely learning based?
Yeah, so the technical idea that makes this work is essentially temporal difference learning. So the idea is that temporal difference learning will basically tell you what is the, for an observed transition, a transition from state at time t to t plus 1, what is the best outcome that you can get at t plus 1? And insofar as the model that makes this prediction, the value function generalized across states, it's basically like that that example that I had mentioned before with the learning from videos, where if you've seen a similar state lead to a different outcome, then you should be able to figure out that a better outcome is possible. And that's basically the central idea that enables this kind of stitching. So let me just rewind a little bit to show you the picture, and hopefully it'll make it a little bit clearer. So this is the picture I had in mind. So if you have two similar states, the green and blue state that led to two different outcomes, the yellow and orange outcome, then through generalization it should be possible to figure out that the green state can lead to the yellow outcome. And that's essentially this recombination of trajectory segments, sometimes referred to as stitching in the literature. And it turns out that regular temporal difference learning, the most classic technique in reinforcement learning, basically enables this.
But usually this comes with the problem of combinatorial explosion, right? So you need to kind of still prune some kind of possibilities, right? And to discriminate and judge between different possibilities at different times, right?
So that's a good question. Classically, people consider this kind of dynamic programming to lead to the curse of dimensionality. With deep reinforcement learning, that tends to be much less of an issue because deep networks generalize. So it's basically the ability of deep networks to generalize that allows you to overcome the combinatorial explosion. Now, there's a lot more nuance to this, and there is actually a real problem there. It's just the problem is no longer the true curse of dimensionality in the sense that there's nothing that actually blows up exponentially with dimensionality, but it does put a heavy burden on the network's ability to generalize effectively. And it turns out that actually a lot of the current challenges, the things that current research in this area is trying to address are some of the generalization challenges around using deep nets for value function estimation. So the challenge is there, but it's not as bad as one might expect from sort of classic curse of dimensionality arguments.
Okay, thanks.
So, please.
Thank you for the talk. I was wondering, it's now all about movements, like getting from one place to another, if I understand correctly. But the robots, yeah, the anti-vectors, for example, they are made for also human interactions, maybe. I was thinking, would it be possible that it also gets some kind of force feedback, or is there a way to use it, to be able to use it in a human interaction environment?
Yeah, that's a good question. I mean, in principle, the techniques that I discussed are, they're not limited to particular choices of modalities. Although, of course, if we're going to talk about bringing in broader sources of data, well, there's a lot more data of videos and images on the web than there is data of force readings. So if you want to make use of more exotic modalities, the data challenges become more severe. I think that there's actually some really interesting research questions in terms of how do we leverage effective pre-training on larger data sets and still adapt to other sensory modalities. It's not at all obvious how to make that work, and I think that's actually a pretty major challenge if we want to start thinking about robotic foundation models with more exotic sensor types. So I think it's a very valid comment. in regard to human interaction more generally, it's definitely possible to utilize techniques like this in human interactive scenarios. In fact, we have some recent work that we recently released on robotic navigation around crowds that require some amount of reasoning about people's personal space and things like that, and social dynamics. And more or less similar techniques can be adapted in that setting. If you have data of interactions around humans, if you can do some online RL where the robot actually interacts with humans, you can adapt in the same way that you adapt to racing around the hallway. Although I'm sure that many other challenges like safety and so on are exacerbated in those settings.
Yeah. Okay, thank you.
Cool. Any other questions? Yes, please. Yeah, you can queue up in here. But let's limit for last 3 questions.
Hello? Yeah, I was wondering, in the case where you may have a complex task that requires a sequence of actions, but you may not have this sequence of actions in the training set. You may have one kind of action. Would this model also generalize for sequences of actions, or maybe it's more convenient to choose follow a hierarchical approach where you may have a high-level planner and then choose these kind of models to follow the plan?
Yeah, that's a good question. I think it depends. So it probably depends a lot on what kind of data you actually have. Some of the things I discussed are essentially hierarchical approaches. So for example, the sub-goal prediction technique from before is essentially hierarchical learning. Let me just pull that up in a second. So the diffusion approach, where sub-goals are predicted based on internet scale data, this one here, you can think of this as a hierarchical method where the diffusion model is basically producing the higher level of the hierarchy, and then a goal condition policy is then carrying out those commands, and that's the lower level of the hierarchy. So it's a kind of planning method, except the higher level is not a motion planner, it's a diffusion model that produces sub-goals. That's a very pragmatic way to go. That said, in principle, as I mentioned in response to the previous question, temporal difference learning can actually recombine individual time steps, although typically you really need short sequences that recombine in different ways. Individual time steps are probably pretty tough if you're doing high frequency control. So there, maybe a hierarchical approach is better.
Okay, thank you.
Hello, thank you for the wonderful presentation. I have a question about the robot foundational model that you are talking about that generalizes through different embodiments. And I'm wondering what would the output be of such a model? For example, if the robot arm has 6 degrees of freedoms compared to 7 degrees of freedoms, then the state space of the robot arm would be very different, and the value function that you learn would not be the same for these robots.
Yep, that's a very good question. So I mentioned this, but I mentioned it very briefly in the talk, that for that particular project, we actually did use the same action space for all the robots. They were all end effector controlled. So that's kind of a cop-out answer. Essentially, we used abstraction to make them look the same, at least on the output side. They all look visually different, of course. That said, other people have trained models that can generalize across different action spaces. The RoboCat paper out of DeepMind did actually control robots with different numbers of degrees of freedom, and they basically used a transformer model that outputs a variable length output. So it is entirely possible to make that work, and you just need a model that can output different numbers of dimensions, and modern transformer models can definitely do that.
Okay, thank you very much.
Perfect. The last question.
Yeah. All right. Thank you for the nice presentation. Maybe what I've seen in the presentation is mostly stable systems from a control perspective, I would say, or at least there's some underlying controller going on. Can you maybe, do you have a comment on how far these, let's say, general models are towards controlling a variety of unstable systems?
Yeah, that's a good question. Let me think about how to answer this. So for the manipulation tasks, almost all the tasks I showed are underactuated in the sense that they involve manipulating objects, and manipulating objects is always underactuated because the objects are not actuated. That said, I think maybe what you're getting at is that most of these are not very dynamic. I mean, whether they're stable or unstable is almost beside the point. They're essentially quasi-static tasks. So at that point, all these notions like underactuation and stability don't really matter, because once you're quasi-static, it's like, yeah, it's a relatively simple problem in that regard. That's not a fundamental property of these methods. I think it's more a property of the fact that, like, for bridge data, the teleoperation device was relatively primitive, so humans couldn't really demonstrate very dexterous or very sophisticated tasks. But there is more recent work that does demonstrate much more physically nuanced tasks with similar kinds of techniques. For example, the Aloha work from Tony Zhao at Stanford, the method is called ACT, shows some very dexterous behaviors. They're still not necessarily highly dynamic, and certainly like notions like stability aren't really that meaningful there. But it's getting much closer to that. I think the issues here are not really fundamental, except insofar as methods that use human collected data, like demonstration data, they require the human to be able to perform the task, and highly unstable tasks are just hard for humans to perform. RL methods can do pretty well there, and in other domains like robotic locomotion, we've been able to get RL methods in the real world to do tasks that require handling pretty severe stability challenges, but that's of course a very different domain. So yeah, what I would say there is, I think this is a valid point. I think it's probably not a fundamental aspect of the learning techniques, but it is very important for the data generation to be able to generate data that deals with that, either through imitation learning, which means good teleoperation so that humans can do it, or through reinforcement learning, which means the robot can figure out how to do it.
Cool, thank you.
Hi, thanks for the talk, Professor. Excellent work on perception and navigation. One thing I felt that you didn't touch on was mapping. So I wanted to know your opinion on this. Do you think that real-time action perception is the way to go? Or maybe mapping is something that could also be added to this?
Yeah, very good question. This is something that I unfortunately couldn't cover in detail for lack of time, but in the navigation work that I showed, the Vint and GNM work, there is actually a higher level planner that decides the individual waypoints. But it doesn't work in the same way as conventional mapping algorithms. So the policy, which is what I focused on, is a goal condition policy. It basically takes in the current observation and a goal image. But the goal image in the longer horizon experiments was not actually the final goal. It was a sub-goal similar to the ones that you're seeing on this slide for manipulation, except the sub-goal was determined by a topological map. A topological map, you can basically think of it as a kind of like a PRM. It's basically a graph that is generated from previous experience seen in that environment. So it's not the same as a fully geometric map that you would build with SLAM. It's a topological map, so basically a graph of previously seen landmarks connected by edges. And each node in that graph is an image. So it is a kind of map, but it is a much more abstract map than the kind that we use for traditional motion planning. And that's because the policy already has a lot of intelligence built into it. The policy doesn't need detailed geometry reconstruction. It basically needs to know that like the hallway is next to the living room. But it is a kind of map, and it was actually used in that work.
Okay, yeah, thank you.
Perfect, thank you very much. So let's thank Sergey again once.
Thank you all for listening.
So thank you very much, Sergey. And now I'm closing the Zoom, but we will send an email for you.
Wonderful,
Okay.
thank you.
Perfect, bye-bye, ciao. Cool, we are end of our workshop, so I hope you enjoyed. And now I have a few closing remarks. Sure. I need to thank first NWO for giving us funding to organize this event. Second, I need to thank the Mind Labs and their members like Petra and Martin. They give us logistic. Okay. And I also thank our students, volunteers. Okay, they enable everything run super smoothly. And finally, I also need to thank our Tilburg University and the Department of Cognitive Science and AI. Did I miss anyone? No? Okay. And of course, workshop organizers, Giacomo and me. Cool. Cool. And now we have one final free drinks for you. That will be an alcoholic. Please enjoy in our bar. But with one reminder, when you leave here, please put your badges on our reception desk. So thank you very much again for joining us today. And let's enjoy one final time for Robotics.